The Dornier 328 is a high-wing, twin-engine turboprop airplane with pressurized cabin designed for medium to short-range operations and capable of short-field operation. The aircraft has a total length of 21.284 meters, a wingspan of 20.976 meters, and an approximate height of 7.239 meters. The fuselage is pressurized between the forward pressure bulkhead located forward of the cockpit and the aft pressure bulkhead, which is located aft of the baggage compartment. Normal pressurization control is automatic, and the conditioned air is provided by two air conditioning packs located in the unpressurized area on top of the fuselage center section. 3 outward opening doors are installed. One Type 2 passenger crew door on the left forward fuselage, one baggage door on the left aft fuselage, and one service door on the right aft fuselage, which can also be used as a Type 2 emergency exit. 2 inward opening Type 3 emergency exits are installed, one on the right side and one on the left side of the fuselage. The flight compartment windows are identified as windshields and side windows. For protection against ice buildup, they are electrically heated by power supplied from the AC alternator system, and for demist, conditioned airflow is provided. Rain removal from the windshields is done by 2 windshield wipers. The passenger compartment has 10 windows on the right side and 11 windows on the left side. The passenger compartment windows are demisted by conditioned airflow between the inner and the outer window pane. 3 pitot probes, 3 static ports, 1 total air temperature probe with 2 independent outputs, 1 ice detector probe, and 2 angle of attack vanes are installed on the forward fuselage. For ice protection, all probes and the 2 angle of attack vanes are electrically heated by power supplied from the DC system. Two landing lights are installed in the left and right main landing gear fairings, and 2 taxi lights are installed on the nose landing gear. 2 wing inspection lights are installed on the forward fuselage, and 1 anti-collision light is installed on the lower center fuselage. Further installed on the aircraft are 2 strobe lights and the 3 navigation lights. The antennas for VHF COM, DME, ADF, ATC transponder, ELT, radio altitude, and marker beacon are externally mounted on the fuselage. The weather radar and the dual glide slope antenna are located in the unpressurized fuselage nose section, and the VHF nav antennas are mounted on the vertical stabilizer. Two mechanically actuated ailerons are installed on the wings. A trimmable servo tab is installed on the left aileron, and a geared tab is installed on the right aileron. Both ailerons are normally connected by the disconnect unit, which enables separation in case one aileron becomes blocked. Hydraulically operated trailing edge flaps are fitted to the wings, and wing de-icing is provided by pneumatic de-ice boots installed on the wing leading edges. All fuel is carried in 2 integral tank groups inside the wings. Each tank group consists of an inboard tank, an outboard tank, and a feeder tank. Fuel supply of both engines from one tank group is possible by selecting cross-feed on the fuel control panel in the cockpit. A connector for pressure refueling is provided on the right-hand wing, and 2 gravity refueling points are installed on top of each wing. The horizontal stabilizer is equipped with 2 horn-balanced elevators that are mechanically actuated through either control column in the cockpit. The elevators are normally connected by a disconnect unit, which also enables separation of the elevator control circuits in case that one becomes blocked. To reduce the pilot's control force, a trimmable servo tab is installed on each elevator. The vertical stabilizer is equipped with a mechanically actuated horn-balanced rudder, which can be actuated by 2 pairs of rudder pedals in the cockpit. To reduce the pilot's control force, the rudder is equipped with a trim tab and a spring tab. The spring tab is only operable at airspeed below 160 knots calibrated airspeed, and mechanically locked above this speed. De-icing for the vertical and the horizontal stabilizers is provided by pneumatic de-ice boots installed on the leading edges. Two wing-mounted Pratt & Whitney PW119B engines are installed, and each engine drives a 6-blade constant-speed propeller made by Hartzell, which can be reversed for braking and ground maneuvering. The propeller blades are equipped with electrical heaters to prevent ice buildup, and engine inlet ice protection is provided by pneumatic rubber de-ice boots. Both engines are equipped with a fire detection and extinguishing system installed in each engine nacelle. An alternator which generates 3-phase wild-frequency 115 200 volts AC electrical power is mounted to each reduction gearbox, and 28 volts DC is produced by a starter generator mounted on each accessory gearbox. The starter generator is also used for engine starting. Electrical power for this purpose is supplied by 2 batteries and/or an external power source. Bleed air from the engine compressors is used for air conditioning, pressurization, and de-icing. To supply the cabin and flight compartment with conditioned air from an air conditioning ground cart, a standard ground connector is installed on the forward lower section of the right main landing gear fairing. The nose landing gear and the main landing gear are twin-wheel designs with oleo-pneumatic shock absorbers. The nose landing gear retracts forward into the fuselage, and the forward nose landing gear doors open and close during extension and retraction. The main landing gear retracts sideways into the lower fuselage main gear bay, and the main gear doors stay open after gear extension. Landing gear extension and retraction is powered by the hydraulic system. All 4 main wheels are equipped with hydraulic actuated brake units, and an anti-skid system provides optimum braking for various runway conditions. Emergency extension of the landing gear is carried out with a hand pump installed in the cockpit. When operated, it will provide pressure to all up-lock actuators and the main landing gear assist actuators. The nose landing gear will extend and downlock by gravity and aerodynamic assistance, whereas the main landing gear has to be forced into the downlock by the assist actuators. The nose landing gear is equipped with a nose wheel steering system, which provides a maximum steering angle of 60 degrees and a centering mechanism that centers the nose wheel for gear retraction after liftoff. A towing adapter is installed on the nose gear for towing operation with a tow bar. The maximum nose wheel deflection during towing without disconnecting the nose gear torque links is 100 degrees to either side. Normal access to the airplane is provided by the passenger crew door on the forward left side of the fuselage, the baggage door on the left rear side of the fuselage, and the galley service door on the right rear side. In addition, 2 plug-type emergency exits for emergency evacuation are installed on the aircraft. A flight compartment door is also provided to separate the flight compartment from the cabin. The passenger crew door is equipped with an integral stairway and a folding handrail. From the outside, the door is closed by first unlocking the hook at the doorstop. By the use of the door handle and the assistance of two gas springs, the door can then be pushed upward until the door structure touches the door frame. It is then locked by pressing against the door and turning the external handle clockwise. For extended parking, the external handle can be locked with a key. The door can be opened by turning the handle counterclockwise and then pulling on the door against the pressure of the gas springs. As the door opens, the handrail unfolds and the flip step opens. When the door reaches its full down position, the hook of the latch mechanism engages. From the inside, the door is closed by first stepping on the pedal, which releases the hook of the lock mechanism, and then pulling the door inward, first by the use of the handrail and then with the door handle. The door is then locked by pushing the door handle into its up position. The door is opened by pulling the door handle down to unlock. The door will open under its own weight and by assistance on the handrail until it locks in the open position. The flight compartment door divides the flight compartment from the passenger compartment. A decompression flap is installed in the lower half of the door and provides pressure compensation in case of a decompression. Note that a key is always required to open the door from the passenger compartment. In case of an emergency, the flight crew can escape using a cockpit hatch installed in the flight compartment ceiling. The plug-type hatch can be opened from inside and outside of the flight compartment. Two Type 3 emergency exits are installed in the cabin, one on the forward right-hand side and one on the aft left side of the fuselage. For extended parking, these exits can be locked with a pin. Note that this pin must be removed before flight. From inside the cabin, these emergency exits are opened by pulling down the handle and lifting the emergency exit clear of the opening. And from the outside, the exit is opened by turning the outboard latch handle. The service door installed in the right-hand rear of the fuselage is used for galley servicing and is a Type 2 emergency exit. From inside the cabin, the service door is opened by pulling the handle to unlock, and then pushing on the door until it reaches its full open position and the latch mechanism engages. The door is closed by first pulling on the latch handle, which unlocks the latch mechanism and releases the door. When the door structure touches the door frame, the handle has to be pushed into the lock position to completely close the door. For extended parking, the service door can be locked with a pin. Note that this pin must be removed before flight. From outside, the door is opened by the use of a rotating handle, which is turned clockwise to unlock the door. The door then has to be moved into its full open position. The door is closed by unlocking the latch mechanism, and when the door structure touches the door frame, the external handle has to be turned counterclockwise to lock the door. The baggage door in the left-hand aft fuselage gives access to the baggage compartment and is opened by turning the handle counterclockwise to unlock the door, which then has to be moved into its full open position. When the full open position is reached, a latch mechanism will engage and prevent unintentional closing of the door. The door is closed by first pressing on the latch mechanism lever, which will release the door. It must then be closed until the door structure touches the door frame. Note that if you pull on the rear side of the door, damage to the door mechanism may occur. Pushing on the door and turning the handle clockwise will then complete the closing process. For extended parking, the door can be locked by a key. In case of an emergency, the door can also be opened from the inside by a red secured handle. Indication for doors and emergency exits is provided on the MFD door system page. If the doors are closed, they will be shown green, and an open status will be shown in red. In addition, a door warning light will illuminate on the red warning panel. The aircraft is certified for two-pilot operation, and the cockpit is arranged so that controls required for operational procedures are in direct reach of each pilot. Two horizontally and vertical adjustable seats with a lap belt and shoulder harness are installed. The armrests of the seats can be folded upward for easier access. To accommodate an observer, an additional foldable seat is installed in the flight compartment entrance, which is also equipped with a shoulder harness and a lap belt. Each control wheel is equipped with various switches for multiple functions, and a stick shaker is mounted to both control columns. The rudder pedals can be adjusted manually, and they provide control for the brakes, rudder, and nose wheel steering. A nose wheel steering tiller for control of the steering at low speeds is installed on the left side console. Controls and indicators for pilot use are located on the instrument panel, which is divided into the captain's and the first officer's instrument panel, with a primary flight display and multifunction display installed on each side, and the center instrument panel, which houses the electronic indicating and crew alerting system, the standby horizon, the standby altimeter airspeed indicator, a clearance delivery head, and landing gear controls for steering, anti-skid, and retraction and extension. The glare shield above the instrument panel contains the flight guidance and display controller, two digital clocks, and the master caution warning switch lights. The overhead panel houses the controls and monitoring panels for the aircraft systems and flight compartment lights. Circuit breakers for essential bus 1 and 2 are provided behind this panel. The center pedestal contains the engine power and condition levers, flap selector, trim normal and standby selectors, the emergency park brake selector, the hydraulic hand pump and control panels for communication, navigation, and various system tests. The side panels contain rheostats for flood lighting, and a nose wheel steering tiller is installed on the captain's side. Normally, caution and advisory messages are indicated on the CAS field, but to minimize nuisance messages and to prevent pilot distraction, certain messages are inhibited while the aircraft is on ground with engines not running, during the takeoff phase and during the landing phase. Each side console has stowage compartments to provide room for a quick donning mask and required manuals. Several different cabin configurations between 27 and 33 seats are available, with single seats installed on the left side and double seats installed on the right side of the cabin. For the stowage of hand baggage, overhead stowage bins are mounted above the right-hand passenger seats. All passenger seat backrests can be adjusted for rake, and except for the front seats, each seat position is provided with a folding table installed in the backrest of the forward seat. The front seats are equipped with tables that are stowed in the armrest. Passenger service units, PSU, are installed above each seat. Each PSU contains a fresh air outlet, a flight attendant call button, a loudspeaker, reading lights, and passenger information signs for no smoking and fasten seatbelts. The flight attendant station is located on the left-hand forward cabin to flight compartment divider bulkhead. It consists of a folding seat with safety harness, the flight attendant control panel for control of the cabin temperature and lighting, a service interphone, and an emergency equipment stowage compartment. The folding flight attendant seat returns to the vertical stowed position when not in use. A standard galley with stowage space for 2 trolleys, 2 hot jugs, 2 food containers, and a waste bin is installed on the right-hand rear section of the passenger compartment. Electrical power for the galley is provided by the DC non-essential bus 2. A flushing lavatory is installed at the rear right-hand section of the passenger compartment. It consists of a toilet bowl and waste tank, a hand wash basin, and a mirror. The flushing liquid is recirculated, and on aircraft with lower serial numbers, AC electrical power is used to drive the toilet pump motor. This means that on these aircraft, the toilet is not operable without AC power available to the aircraft buses. Additionally, a PSU, a waste bin, a paper towel dispenser, and a smoke detection system is installed in the lavatory. The Environmental Control System, ECS, uses high-pressure bleed air or low-pressure bleed air from the engines or the APU, which is supplied to the 2 ECS packs above the fuselage. Bleed air from the left and right-hand side is connected via a cross-bleed line, which is controlled by a cross-bleed valve. The valve can be operated by the flight crew to supply both packs from only one engine or the APU if installed. Cooling and heating is produced via 2 independent environmental control system ECS packs, which are mounted on top of the fuselage forward of the wing. Each pack consists of a cold air unit, a dual heat exchanger, a condenser water extractor, various control and regulating components, and a ground cooling fan, which provides cooling air to the heat exchanger at airspeeds below 120 knots. Via ducting, the conditioned air from the ECS pack is routed to the cabin and the flight compartment. The air is then distributed into these compartments via floor and ceiling outlets. In addition, the toilet compartment, the captain, the first officer, and each passenger seat position is supplied with air through an adjustable outlet. Air for windshield demist is also provided via the left and right window demist outlets. The used air is extracted from the cabin by the use of floor-level openings on the side of the passenger compartment. Two electrically driven recirculation fans are installed in the underfloor area. The aft fan and check valve supplies the passenger compartment, and the forward fan and check valve supplies the flight compartment. The fans recirculate used air from the cabin underfloor in order to maintain the required level of ventilation. A ground connector is installed on the forward lower side of the right-hand landing gear fairing, which can be used to supply conditioned air to the flight and passenger compartments when on ground. Two avionic fans are installed to provide a certain amount of cooling to the avionic compartments. The forward EFIS fan draws air from the flight compartment underfloor area and blows it onto the display units in the cockpit. The aft avionic fan sucks air from the avionic racks and the instrument panel and exhausts it into the cabin underfloor area. Control and indication for the environmental control system is done via the ECS panel and the ECS page on the multifunction display. The left and right air conditioning packs are controlled by the left and right pack push buttons on the ECS control panel. When the buttons are pushed, the off light will extinguish and the vertical bar will illuminate. Then the respective flow control and shutoff valve opens, providing bleed air to the pack and therefore into the cabin, and at the same time the symbol on the system page will move into the vertical position and turn green. If the pack switch is selected to off, an amber pack in-op message will appear on the ICUS, or no bleed air is available to the pack. An amber pack in-op message will appear on the ICUS except with weight on wheels and engine low pressure compressor speed below 64%. With the bleed air flow mode switch selected to high, bleed air flow to the packs can be increased if demanded. Temperature control is also done via the ECS panel. Two temperature controllers regulate the temperature of the air supplied to the passenger and flight compartments automatically to the level set with the cabin and the flight compartment temperature selector. Within certain limits, the passenger compartment temperature can also be controlled from the flight attendant panel. In case of a failure within the automatic temperature control systems, the respective system can be selected to manual to directly drive the temperature control valve. In case of a temperature controller failure or an inappropriate temperature selection in manual mode, a backup protective function is provided by the duct limiter, which will limit the supply temperature to 80 plus or minus 5 degrees. The recirculation and avionic fans are also controlled from the ECS panel. These fans are always on during normal operation, and therefore the switches will be dark in the on position. In case of failure of one or both recirculation fans, a message will illuminate on the ICUS, and the ECS page will indicate the failed fan. In case of an EFIS fan failure or of an avionic fan failure, the fail light on the switch and a message on the ICUS will illuminate for the respective fan. The air conditioning system delivers bleed air to the pressurized section of the fuselage. Pressurization is automatically controlled by a digital electro-pneumatic cabin pressure control system, and for backup, a manual-operated pneumatic control system is provided. Both systems have override safety devices installed on both outflow valves, which limits the positive pressure differential to 7 plus or minus 0.1 psi, the negative pressure differential to minus 0.3 psi, and the cabin altitude to a maximum of 14,500 plus or minus 500 feet. Further, a backup indication module is installed to provide the crew with cabin altitude, cabin vertical speed, and excessive cabin altitude warning on the ICUS when the system is operating in manual mode. The CPCS receives signals from the two air data computers, which provide information on aircraft pressure altitude, barometric correction, and aircraft vertical speed. The flight management system that supplies flight time remaining, time to top of climb, cruise flight level, and landing elevation. The proximity switch electronic unit, PSEU, which is part of the landing gear position and warning system, and also monitors passenger, crew, service, and cargo compartment door proximity sensors. This prevents pressurization if one or more of the doors are not properly closed. When the power levers are advanced for takeoff, the power lever microswitches will close and initiate the pre-pressurization sequence, and after liftoff, the landing gear weight on wheels relay initiates the after takeoff pressurization. At aircraft touchdown, the landing gear weight on wheels relay initiates the after landing depressurization sequence. The digital controller consists of a front panel and 4 plug-in electronic modules with an integrated manual selector valve. Via the 3-position elevation set switch, which is spring-loaded to the center position, the required elevation can be set on the landing elevation window in increments of 100 feet in the range between minus 1,500 and plus 14,000 feet. The switch must be held into the desired position, and the initial speed of change will be 200 feet per second, and increase to 1,000 feet per second after 5 seconds. The auto manual switch light is used to select the desired mode, and the manual operating mode is indicated by the manual light on the switch face. By the use of the manual cabin altitude control knob, the pilot can then pneumatically control the operation of the forward pneumatic outflow valve. The cabin dump switch can be used to dump the pressure in the cabin and flight compartment. When pushed, it will automatically open both outflow valves. In automatic mode, the pressurization control is completely automatic. The schedule is designed to provide a maximum cabin climb or descent rate of not more than 550 feet per minute, and a cabin altitude of 5,325 feet at a flight altitude of 25,000 feet with a differential pressure of 6.62 psi. At 31,000 feet, this will provide a cabin altitude of 8,000 feet with a differential pressure of 6.75 psi. Five dashes are the default value on the landing elevation display window and on the CPCS page. If the crew fails to select the landing elevation, a blue No Valid Landing Elevation message will appear on the CAS field. The manual mode operates completely independent from the automatic mode, and the flight crew must set a rate of change using the manual cabin altitude selector. Full up will produce a rate of climb of 2,500 feet per minute, and full down will produce a descent rate of 1,500 feet per minute. The flight director, autopilot, and yaw damper are controlled from the flight guidance controller installed on the glare shield panel, and mode indication is provided on the controller and on the primary flight display. Note that if only the yaw damper is selected, no indication is provided on the primary flight display. Controls for the following modes are located on the guidance controller: heading, navigation, approach, back course, bank, standby, flight level change, vertical speed, altitude, vertical navigation, autopilot, yaw damper, PFD selection, and the pitch wheel. When electrical power is applied to the aircraft, the flight guidance system initiates an automatic power-up self-test, which takes approximately 60 seconds on ground and 20 seconds when airborne. If a failure is detected, an amber FGC fail message will be displayed on the CAS field, and if the flight director does not work, an amber flight director fail message will be displayed on the PFD. The heading hold mode is the basic lateral mode, and it is enabled when the bank angle is less than 6 degrees. No lateral mode is selected, and the autopilot is engaged. If these conditions are satisfied, the airplane will roll wings level. A roll annunciation will be displayed on the PFD, and the standby button will be illuminated on the flight guidance controller. The roll-hold mode is enabled when the bank angle is more than 6 degrees, but less than 35 degrees. No lateral mode is selected, and the autopilot is engaged, and the roll maneuver was initiated with touch control steering, TCS. If these conditions are satisfied, the airplane will maintain the desired bank angle. A roll annunciation will be displayed on the PFD, and the standby button will be illuminated on the flight guidance controller. If the TCS button is used again, the roll and the autopilot select indication will extinguish, and the TCS indication will illuminate. The aircraft then can be manually controlled. When TCS is released and the bank angle is above 35 degrees, the autopilot will roll the aircraft to 35 degrees roll. The heading select mode is used to select and intercept a magnetic heading, and it is indicated by a heading message on the PFD. Heading bug selection is done via the heading knob on the display controller, and the maximum angle of bank during a turn is limited to 27 degrees. However, by pushing the bank button, the maximum angle of bank can be limited to 17 degrees in heading select mode. The heading select mode is cancelled by either pushing the heading button again, by the automatic capture of any other lateral mode, by coupling to the cross-side PFD or pushing the standby button, by changing the symbol generator driving the coupled PFD, by the selection of the go-around button, or on ground, by selecting takeoff reference data. Selecting the nav button allows for automatic intercept, capture, and tracking of selected VOR, localizer, or ILS signals. The VOR mode is selected by first tuning the desired VOR frequency, pushing the VL button to select VOR as the navigation source, selecting the desired course to or from the station, and then setting the desired intercept heading for the course. If the nav button is then pushed, and the aircraft is outside the normal VOR capture range, a white VOR annunciation will appear on the PFD. When the airplane now approaches the selected course and enters the capture phase, the green heading and the white VOR message will extinguish, and a green VOR message will start to flash for 5 seconds. The flight guidance computer will now generate the proper roll commands to track the selected radial. If the pilot wishes to select the FMS as his navigation source, the nav mode is used as in VOR mode, except that the navigation source has to be selected to FMS. When the nav mode is then engaged, an LNAV message will be displayed on the PFD. The VOR and the FMS LNAV mode can be cancelled by either pushing the nav, heading, approach, or standby button, by changing the navigation source for the coupled PFD, by coupling to the cross-side PFD, by changing the symbol generator driving the coupled PFD, or by selecting Go Around. The VOR mode can also be canceled by changing the VOR frequency. The VOR approach mode works exactly the same as the VOR mode, except that the approach button has to be pushed, a VOR with an asterisk indication will appear, and an MDA is set on the PFD altitude tape. In this mode, the gains in the flight guidance computer are changed to optimize system performance. The localizer mode is selected by first tuning in the desired localizer frequency, pushing the VL button to select ILS as the navigation source, selecting the applicable localizer inbound heading, setting the desired localizer intercept course, and selecting the appropriate minimum descent altitude on the PFD. If the nav button is then pushed and the aircraft is outside the normal localizer capture range, a white localizer annunciation will appear on the PFD. When the airplane now approaches the selected course and enters the capture phase, the green heading and the white localizer message will extinguish, and a green localizer message will illuminate. The flight guidance computer will now generate the proper roll commands to track the selected localizer signal. The localizer mode can be canceled by either pushing the nav, heading, back course, or standby button, by changing the navigation source for the coupled PFD, by coupling to the cross-side PFD, by changing the symbol generator driving the coupled PFD, or by selecting Go Around. The localizer mode can also be canceled by changing the localizer frequency. The back course approach mode allows for automatic intercept, capture, and tracking of a localizer back course signal, and works exactly the same as the localizer mode, except that the back course button has to be pushed, and a back course indication will appear. The back course mode can be canceled by either pushing the back course, nav, heading, approach, or standby button, by changing the navigation source for the coupled PFD, by coupling to the cross-side PFD, by changing the symbol generator driving the coupled PFD, or by selecting Go Around. The back course mode can also be canceled by changing the localizer frequency. The Instrument Landing System Approach mode allows the pilot to fly a fully coupled ILS approach, and it is selected by first tuning in the desired localizer frequency, pushing the VL button to select ILS as the navigation source, selecting the applicable localizer inbound heading, setting the desired localizer intercept course, and selecting the appropriate decision height on the PFD. If the approach button is then pushed and the aircraft is outside the normal localizer and glide slope capture range, a white localizer and glide slope annunciation will appear on the PFD. When the airplane now approaches the selected course and enters the capture phase, the green heading and the white localizer message will extinguish, and a green localizer message will illuminate. The flight guidance computer will now generate the proper roll commands to track the selected localizer signal. At glide slope capture, a green glide slope annunciation will replace the vertical mode annunciation, and the flight guidance computer will now generate the proper pitch commands to follow the glide slope. The ILS mode can be canceled by either pushing the standby button, selecting any vertical or lateral mode, by changing the navigation source for the coupled PFD, coupling to the cross-side PFD by the use of the couple button, by changing the symbol generator driving the coupled PFD, or by selecting Go Around. The ILS mode can also be canceled by changing the localizer frequency. The aircraft communication system can be divided into the following sections: the speech communication, the data communication and automatic calling systems if installed, the passenger address and entertainment system, the audio integrating system, the static dischargers, the audio monitoring system, and the integrated automatic tuning system. For system redundancy, the following buses are provided: the primary radio system bus, the secondary radio system bus 1, the secondary radio system bus 2, the audio bus 1, and the audio bus 2. The Radio Management Unit, RMU, tunes and controls the COM and NAV radio systems via the radio service buses. The audio integrating system controls and monitors the audio signals of the COM and NAV systems via the audio buses. The aircraft has two VHF COM systems installed, designated as VHF-1 and VHF-2, which operate in the frequency range of 118 to 136.975 MHz. Two integrated communication units, ICUs, contain all required modules for reception, transmission, and digital audio interfacing. The number 1 ICU is located in the left-hand avionic rack, and the number 2 ICU is located in the right-hand avionic rack. To prevent blocking of a communication channel, the ICU has an automatic timeout function, which will automatically return the unit to receive mode after about 2 minutes of continuous transmission. The VHF COM system has two identical antennas. The number 1 antenna is located on the upper fuselage, and the number 2 antenna is located on the lower fuselage. A COM1 hot button on the instrument panel provides the crew with the ability to use the VHF-1 COM system without switching on the complete aircraft 28-volt DC electrical power system. When the COM1 hot button is pushed, power from the DC hot bus 2 is supplied to the clearance delivery head, the number 1 VHF COM system, and the number 2 audio control panel. With aircraft 28-volt DC electrical power on, the VHF COM systems are normally controlled with the Radio Management Unit's RMU. For transmitting, the operator must push and hold down the push-to-talk switch on the control wheel or on the hand mic. The passenger address system allows the flight crew to communicate with the flight attendants and the ground crew, and to make announcements to the passengers via loudspeakers installed in the passenger compartment. The system consists of the PA amplifier installed in the left-hand avionic rack, which controls the system and also generates the no smoking and fasten seatbelts chimes, the calls control panel, the flight attendant phone, and the ground crew jacks located on the ground control panel forward of the DC external power connector. The calls control panel is installed in the overhead panel. When the emergency button is pushed, emergency communication with the flight attendant station is possible. If the emergency button is pushed again, this mode is canceled. When the light flashes and a chime is audible, an emergency call from the flight attendant has been received. When the cabin button is pushed, normal communication with the flight attendant station is possible. If the cabin button is pushed again, this mode is cancelled. When the light flashes and a chime is audible, a call from the flight attendant has been received. When the ground button is pushed, communication with the ground crew is possible. If the ground button is then pushed again, this mode is cancelled. When the light flashes and a chime is audible, a call from the ground crew has been received. The flight attendant phone enables the cabin crew to communicate with the flight crew and with a second cabin attendant phone at the galley if installed, and to make announcements to the passengers. A push-to-talk switch on the inside of the handset has to be pushed and held down to operate. If the phone is taken off the cradle and the emergency button is pushed, the LED above the button will be flashing and emergency communication with the flight crew is enabled. If the phone is put back on the cradle, this mode is cancelled. When the flight crew calls the cabin in case of an emergency, a chime will be audible and the LED will be on steady. If the phone is then picked up from the cradle and put back down, the mode is cancelled. If the phone is taken off the cradle and the FLT button is pushed, the LED above the button will be flashing and normal communication with the flight crew is enabled. If the phone is put back on the cradle, this mode is cancelled. When the flight crew calls the cabin, a chime will be audible and the LED will be on steady. If the phone is then taken off the cradle and put back on, the mode is cancelled. PA can be selected to make passenger announcements, and the attendant button on the phone is used to call or receive calls from the second flight attendant phone if installed. The ground crew can communicate with the flight crew via the ground crew jacks installed on the ground control panel. An audible signal to the flight crew can be generated with the call button. The airplane is equipped with an audio integrating system, which is controlled by the two audio control panels installed in the center console. It allows for interphone communication between the captain and first officer, the flight attendant positions, and the ground crew. Further, it allows for voice intercommunication via the aircraft radio communication systems and monitoring of all audio outputs of the communication and navigation system. The audio control panel has 6 transmit buttons that must be pushed in to select the appropriate transceiver or interphone channel. When the emergency button is pushed, the microphone signals are directly connected to the selected comm transmitter, and the received audio signals are connected directly from the receiver to the headphone or speaker. The headphone volume is controlled by the headphone audio control. The COM and NAV audio on-off volume control buttons are used to select the connected COM-NAV receivers. When the buttons are in, they are in the off position, and when in the out position, the applicable channel is on, and the volume can be adjusted. The maximum level is at the full clockwise position, except for the DME and MLS selectors, which are dual-channel selectors with each channel at its minimum position when the selector is centered. When turned to left or right, only the volume of one channel will increase. The microphone mask selector is used to choose which microphone is connected to the transmitter. When the selector is pushed in, either the headset or hand microphone is connected to the transmitter, and when the button is pushed out, the oxygen mask microphone is connected, and the speakers are switched on. Static dischargers on the aircraft flight control surfaces are installed to discharge the airplane electrostatic charges accumulated during flight. The static discharger is a graphite-coated rod of aligned fibers with a brush of fine wires at the discharger tip, which discharge the accumulated electric charges into the air. A cockpit voice recorder, CVR, is installed in the aircraft tail to record radio communication and communication between the flight compartment, the cabin, sounds in the flight compartment, and passenger announcements. An impact switch is installed next to the CVR to cut electrical power and to prevent the CVR from further recording if the aircraft sustains a force greater than 3 Gs in flight direction. The crash and fire-resistant CVR is a 4-channel tape recorder with a continuous recording duration of 30 minutes. An underwater locator beacon is installed on the CVR, which will transmit a 35 to 40 kHz wobble tone if submerged. The control unit installed in the cockpit contains a test button to perform a self-test of the CVR and an erase button to erase all recording. The microphone monitor indicates the recording level and also indicates a successful self-test. By connecting a headphone, the CVR recording can be monitored. For recording conversation and sounds within the cockpit, a remote microphone is installed above the standby compass. For radio system tuning, 2 RMUs are installed in the cockpit. RMU 1 normally controls the left-hand radios, and RMU 2 the right-hand radios. RMU cross-side control is possible by pressing the 1-2 switch on the RMU. For auxiliary control and backup purposes, a clearance delivery head capable of controlling COM1 and NAV1 radios is installed on the instrument panel. The RMU is the central control system for the VHF communication system, the VHF navigation system, the ATC transponder system, the ADF system, the TCAS system, and the MLS if installed. The RMU has 2 COM-NAV frequency transfer buttons, 10 line select keys, 8 function keys, a large and a small control knob. A COM or NAV frequency can be pre-selected by pushing the applicable COM or NAV line select key. The desired frequency can then be entered by using the tuning knobs, and as soon as the applicable transfer button is pushed, that frequency will become active. Be aware that pushing both transfer buttons at the same time while on ground will cause the RMU to enter the airplane maintenance mode. An ADF frequency or transponder code is entered by selecting the applicable line select key and directly entering the desired frequency. The squelch button on the RMU opens the squelch circuit and allows any signal present in the radio to be heard. The dim button allows for selection of the display brightness via the small tuning knob, and the 1-2 button allows for tuning of the cross-side RMU frequencies. When this button is pushed, the legend color will change to magenta, and cross-side tuned frequencies will be displayed in amber. By pushing the storage button, pre-selected frequencies can be stored in the RMU memory, and pushing the ident button will put the ATC transponder into the identification response mode. Pressing the page button on the RMU allows access to all pages such as the engine backup pages or the navigation pages. The test button allows for testing the selected radio system enclosed within the cursor box. The test button must be pushed and held for the duration of the test. The DME button is used to deslave the DME from the VOR frequency, and it allows for a separate selection of DME channels without changing the VOR frequency. RMU radio tuning can also be performed by the flight management system. When the FMS is used to tune the RMU, the frequencies tuned by the FMS auto-tune function will be displayed in magenta. The electric power systems of the Dornier 328 include the AC power supply system and a 28-volt DC power supply system grounded to the aircraft structure. The AC power supply system has two main subsystems: the AC alternator system, which is a three-phase 115-volt AC unregulated frequency power supply system, and the AC inverter system, consisting of a 115-volt AC 400 Hz regulated frequency and a 26-volt AC 400 Hz regulated frequency power supply system. Two separate three-phase AC bus bars are supplied with 115-volt AC power by two engine-driven AC alternators. The frequency is unregulated and depends upon the speed of the propeller. It will be within the range of 290 to 445 Hz at propeller speeds between 65 and 100% revolutions per minute. Parallel operations of the alternators is not possible. The AC power from the alternator system is used to supply the electrically heated anti-icing system and the main hydraulic pump. The AC alternator system has the following main components: left and right-hand alternator, alternator control unit or ACU, current transformer unit or CTU, alternator line relays or ALR, and the alternator left and right-hand control buttons. The control of the AC alternator system is made with DC power from the 28-volt DC main bus 1 and 2. If both engines are running, the alternator number 1 and 2 are already producing 115-volt AC power offline. When the switch light of the left-hand alternator is pushed, the alternator number 1 is switched on. At the same time, the logic circuit of the alternator control unit switches in the alternator line relay, and the alternator number 1 goes online. For the right-hand alternator, the right switch light will be pushed, and in the same sequence as before, the alternator number 2 goes online. Both alternators are now online. Each of them are supplying its adequate AC bus. If a failure is found in the system during operation, the logic of the alternator control unit interrupts the voltage to the alternator line relay. The alternator goes offline and the fail indication comes on. The no longer supplied AC bus can now be cross-fed via the bus tie. When the bus tie switch light is pushed, the alternator line relay will close the relay for the cross-feed. The alternator, which is still in operation, will now supply both AC buses. The AC alternator system is controlled by the electric control panel. The AC alternator system status message is located on the ICUS display and the multifunction display. The caution messages are displayed on the crew alerting system field of the primary ICUS page and on the electric system page of the pilot and co-pilot multifunction display. On the ICUS display, the following messages may be visible: left AC volt fail. One or more phases of left-hand alternator failed. Right AC volt fail. one or more phases of right-hand alternator failed. Left alternator fail, left-hand alternator failed. Right alternator fail, right-hand alternator failed. On the multifunction display, the following messages may be visible. AC bus 1 and 2 synoptic for the AC volt within the limit. An amber AC bus 1 and 2 synoptic for the AC volt out of the limit. AC phases left and right-hand digital readout with an AC phase fail indication. Alternator operation fail. AC bus tie closed or AC bus tie open. The static inverter system converts DC electric power into a single-phase regulated AC power. The output 26-volt AC 400 Hz and 115-volt AC 400 Hz has a stabilized voltage and frequency. This output power is used to supply the indication equipment and navigation systems. The AC inverter system has the following main components. Inverter 1 and 2 switch light. 2 inverters, and 2 relays. When the switch light of the inverter number 1 is pushed, the inverter is switched on. If the output voltage and the frequency of the inverter is within tolerance, the relay for the AC buses will be energized. The relay switches the output voltage to the 115-volt AC and 26-volt AC buses. At the same time, the off indication of the switch light goes out. As long as the second inverter isn't switched on, the primary inverter supplies both left and right constant 400 Hz frequency AC buses. When the second inverter switch light is pressed, the coil of the right relay will be energized, and the right AC buses are now supplied via the inverter number 2. The inverter system is operated by the inverter 1 and 2 switch lights. If 28-volt DC power is available, the inverter will operate when the switch light is pressed. The inverter can be manually switched off via the switch light. If an inverter fails, it will be indicated by the switch light. The AC inverter system status message is located on the ICOS display and the multifunction display. The caution messages are displayed on the crew alerting system field of the primary ICOS page and on the electric system page of the pilot and co-pilot multifunction display. On the ICOS display, the following messages may be visible. Inverter 1 fail. Inverter 2 fail if the inverter has failed. Inverter bus 1 fail. Inverter bus 2 fail if no power is available or the bus has failed. On the multifunction display, the following messages may be visible. Inverter bus 1 and 2 synoptic for the 26-volt AC within the limit. Amber inverter bus 1 and 2 synoptic for the 26-volt AC out of the limit. Inverter left and right-hand digital readout. Inverter bus 1 and 2 synoptic for the 115-volt AC within the limit. Amber inverter bus 1 and 2 synoptic for the 115-volt AC out of the limit. Inverter left and right-hand digital readout, and an operation status if the inverter fails. external power to the AC and DC electrical system can be provided via the DC external power connector installed on the left-hand fuselage nose section and the AC external power connector installed inside the forward left-hand main gear fairing. A three-phase 115-volt AC ground power can be connected to the airplane via the external power connector forward of the left main gear. With the DC external power selected on and functioning, 115 volts AC can then be supplied to the aircraft AC bus 1 and 2. Switch-in of the batteries is prohibited for safety reasons. The AC external power indication is available from the electrical system page and the external power switch. The voltage is monitored by the ground power protection unit, and if it exceeds certain limits, the ground power is taken offline automatically. For ground handling or engine starting, a 28-volt DC ground power can be connected to the aircraft via the connector on the left-hand nose section. With the external power on and operating within its parameters, the green available light illuminates. And if selected on, the ground power will then supply power to the aircraft buses. This will be indicated by the on light in the switch light. At the same time, the generators and batteries are disconnected from the buses to prevent possible damage in case they are selected on. With the external power connected and all parameters within limits, the BPCU and the ground power protection relay release control for switch-in, which is indicated by a green available light on the external power switch light, and the not used light on the DC ground control panel. When the external power is then selected to on, all aircraft DC buses will be supplied with DC external power. At the same time, the generators and batteries will be disconnected from the buses and inhibited as long as external power is on. This will be indicated by the on light on the switch lights and the MFD. In case of overvoltage, undervoltage, or reverse polarity, the BPCU and the ground power protection relay will automatically disconnect the ground power from the aircraft. Emergency equipment is installed in different locations in the flight compartment and cabin. Actual locations may vary between different aircraft and aircraft operators. In the flight compartment, an emergency axe, a fire extinguisher, and a PBE are installed inside the flight compartment step stowage. Also installed in the flight compartment are 3 sets of smoke goggles, 3 quick-donning oxygen masks, and 3 crew life vests, 1 for each flight crew member, and a flashlight located on the left-hand console. For flight crew escape assistance, an escape rope is installed inside the crew hatch. This is required because the hatch is more than 1.8 meters above ground. In the cabin, a fire extinguisher, a PBE, a flashlight, and a crew life vest are installed below the flight attendant seat. In addition, a fire extinguisher, a PBE, and a first aid kit are installed in the forward galley bulkhead. 3 first aid oxygen masks, 1 demonstrator oxygen mask, 3 pairs of fire protection gloves, and 3 children's life vests are installed in the forward tapered hat rack. Passenger life vests are installed under the passenger seats. The exit indicators and locators installed in the passenger compartment give clear indications about emergency exit location during day and night, and a lighted emergency escape path installed at the edge of the right seat pedestal shows the way to the next emergency exit. These lights are powered from separate battery packs. To provide oxygen to all passengers and the flight attendant in case of a rapid decompression, drop-down oxygen masks are installed in the PSUs above the passenger seats and in a drop-out box above the flight attendant seat. The fire protection system of the Dornier 328 consists of a fire detection system and a fire extinguishing system. The engine fire detection system indicates the presence of overheating or fire in the engine fire zone. An endless loop fire wire sensing element is installed in the fire zones on each engine. This temperature-sensitive element is connected to the control unit, which monitors the change in the electrical properties of this element. If a fire or overheat signal is detected from the sensing element, for example, the left-hand engine, the control unit triggers the relevant aural and visual warnings. Two fire extinguisher bottles are installed in each engine nacelle. They are designed to put out a fire in less than 1 second as soon as the fire extinguishing system is activated. A detonator in the bottle is fired electrically from the fire warning extinguishing panel. This causes the fire bottle to discharge its contents of extinguishing agent under high pressure to put out the fire. This is accomplished by stainless steel distribution pipes and nozzles which direct the extinguishing agent to the fire. The temperature-compensated pressure switch is mounted on the fire bottle and monitors whether the fire extinguisher is fully charged or not. It closes a switch contact when a small amount of pressure loss has accrued at any ambient temperature. Each fire bottle is provided with a discharge indicator. The indicator is fitted flush with the aircraft's skin and connected by a pipe to the filler safety relief valve on the fire bottle. If the fire bottle suffers overpressurization, a ruptured disc installed in the filler safety relief valve will burst. The disc is designed to burst at a temperature inside the bottle equivalent to an ambient temperature of 150 degrees Celsius. The contents of the bottle will eject a green disc installed in the discharge indicator, exposing a red indicator bowl providing visual evidence of discharge. Engine fire is indicated for the left and right-hand engine by the engine left-hand fire button and the engine right-hand fire button. The fire buttons are protected by a guard, which prevents inadvertent operation. A short circuit in the engine fire detection system is indicated by the illumination of the loop fail light. The left loop fail light for the left engine detection system and the right loop fail light for the right engine detection system. There are 4 fire bottle discharge buttons, each one responsible for indicating one of 4 engine fire extinguishing bottles. Each button shows a green squib light when the system is ready to discharge, a white discharge light when the system has discharged, and a green agent light for the system test when the capacity check of the engine fire bottle is satisfactory. 2 test switches are provided on the fire warning extinguishing panel for testing the left-hand and right-hand systems. If an engine fire occurs, for example at the left-hand engine, the master warning light flashes. An aural warning on the loudspeakers and headphones comes on. The left engine fire light on the red warning panel comes on, and the left engine switch light comes on. The pilot now opens the guard of the switch light, which prevents inadvertent operation, and presses and releases the engine fire switch light. When the left engine fire switch light is pressed and released, the left engine DC generator switches off. The fuel shutoff valve of the left engine closes. The left engine bleed air shuts off. The left propeller feathers. The auto ignition switches off. And the squib field on the fire extinguisher bottle number 1 and 2 comes on by a green light indication. The detonators are now armed. If the squib switch light is now pressed, the detonator in the fire bottle fires. This causes the fire bottle to discharge its contents of extinguishing agent under high pressure to put out the fire. When the bottle is discharged, the discharged field on the switch light comes on white. Afterwards, when the engine area is cooled down, the fire warning and fire warning switch light goes out. When the test switch is set to the fail agent position and the fire bottle has not lost pressure, the agent field of the bottle number 1 and number 2 comes on. Also, the loop fail light comes on. If pressure is lost in a bottle between 30 and 100 psi, the agent field light goes out, and at the same time the appropriate discharged field light comes on. When the test switch is set to the fire squib position, the fire bell sounds in the cockpit. The master warning light flashes. The engine fire warning light at the red warning light panel comes on. The engine fire button at the engine fire warning and extinguishing panel comes on when the fire detection loops are okay. And the bottle number 1 and number 2 squib field light will illuminate if there is no short circuit in the squib. If a short circuit occurs in the squib field light will stay off. An ionization, ambient-type smoke detector is installed in the lavatory to alert the flight crew when smoke is present in that area. If smoke is detected in the toilet, the smoke lavatory message on the caution and advisory system field on the ICUS comes on. If the detector or the associated circuit fails, the smoke lavatory fail message on the caution and advisory system field on the ICUS comes on. This lesson provides information about the flight control system of the Dornier 328 aircraft. The flight control system can be divided basically into 3 sections: the primary flight control system, the secondary flight control system, and the spoiler system. The aircraft primary flight controls consist of conventional ailerons, elevators, and rudder. The primary control surfaces are moved manually by linkage systems consisting of cables, pulleys, levers, and rods. The secondary flight controls of the Dornier 328 consist of aileron, elevator, and rudder trim systems and trailing edge flaps. The aircraft is trimmed in the 3 axes by electromechanical actuators driving trim tabs. The flap system consists of 1 flap section on the trailing edge of each wing half. The 2 flap sections at the right-hand and left-hand wing are mechanically linked and are driven hydraulically. For improved performance, roll spoilers and optional ground spoilers are installed. The roll spoilers move simultaneously with the ailerons to assist their function. Both sets of spoilers are located on the top surface of the wing and are driven hydraulically. A gust lock system provides aileron and elevator locking for parking by a lever in the flight compartment. The rudder control system is equipped with a hydraulic gust damper, which prevents damage to the structure when the aircraft is parked in gusty conditions. Let's take a closer look at the aileron control system. The aircraft is controlled about the roll axis by a conventional aileron control system. 2 ailerons are installed, one on the outboard trailing edge of each wing. The ailerons are manually operated by dual-control wheels. The linkage from the control wheels to the ailerons is by an arrangement of pulleys, cables, quadrants, push-pull rods, levers, and bell cranks. The maximum aileron movement is 30 degrees up and 25 degrees down. The captain's and first officer's aileron control runs are joined by a disconnect unit. This unit allows the two controls to be separated should one control become jammed. The unit has two halves which are held engaged by a spring and cam arrangement. Under normal operating conditions, the two halves of the unit are firmly engaged and move together as a single unit. Should one of the aileron control circuits jam, the two halves can be disconnected from each other by the application of a higher-than-normal force at a control wheel. The disconnect force is approximately 39 decanewton, or 87.7 pounds. In this situation, the captain's control circuit is connected to the left aileron only. The first officer's control circuit is connected to the right aileron only. The aircraft can be controlled about the roll axis using the remaining free control wheel. Once the aileron disconnect system has been activated, it can only be reset on the ground. The Dornier 328 can be trimmed about the roll axis by a trim servo tab located on the inboard trailing edge of the left aileron. The tab is driven by an electrically powered actuator installed in the trailing edge of the wing. The actuator is controlled by either a main or a standby aileron trim switch at the trim control panel in the center pedestal. The aileron trim setting can be monitored at the ICUS panel. A standby aileron trim system provides aileron trimming when the normal aileron trim system has failed. The standby aileron trim switch is installed in the forward right-hand section of the trim control panel. Activation of the standby switch initiates the lockout circuit, which disables the normal aileron trim system. The normal aileron trim system can be re-enabled by pressing the reset switch light. The aileron trim system can be tested through a trim test push switch installed in the forward left-hand section of the center pedestal. Pushing and holding of the trim test switch with the following activation of the normal aileron trim switch results in reverse aileron trimming operation. This indicates a serviceable aileron trim system. The fuel storage system of the Dornier 328 consists of two separate wing tank groups, in the left wing and in the right wing to supply the related engine. Each wing tank group consists of an inner tank with a capacity of 990 kilograms, an outer tank with a capacity of 633 kilograms, and the feeder tank with a capacity of 85 kilograms. The wing tank groups can take a total fuel quantity of 3,416 kilograms. The fuel tank venting system provides the inner and outer tanks with atmospheric air pressure at all times, regardless of whether the aircraft is on the ground or in flight. Bleed holes between the feeder, outer, and inner tanks provide pressure compensation within each wing tank group. Thermal expansion of the fuel and air will also be compensated by the venting system. Without a tank venting system, each flight level change would cause structural deformations to the wing, created by the pressure difference between ambient air and tank inner pressure. Drain valves are installed on the underside of each wing tank. Condensed water, which has a higher specific weight than fuel, will collect at the deepest point of the tank where the drain valves are located. The drain valves are opened so that the condensed water and residual fuel can be drained from the applicable tank. These drain valves are also used to take samples for the fuel contamination test. During operation of the aircraft, an imbalance between the left and right wing tank groups can occur. In case of such an imbalanced situation, the pilot can correct the fuel quantity by switching over of the fuel transfer switch on the fuel control panel to the left-hand engine. The crossfeeder valve will open. From this moment, the right wing tank group will supply both engines. The motive fuel shutoff valve of the left wing tank closes to prevent fuel flow to the jet boost pump. Afterwards, when the imbalance of the fuel quantity is corrected, the pilot switches the fuel transfer switch back to the middle position to stop the transfer operation. The pilot can check the remaining fuel quantity while in the cockpit on the fuel system page of the multifunction display, or the ICUS display, or outside of the aircraft at the refuel-defuel panel, if the master switch is set to the on position. At the refuel-defuel panel, the pilot can pre-select the required fuel quantity, up to a maximal load of 3,311.3 kilograms in the automatic mode, which will then be displayed. The pilot can also pre-select the fuel quantity with the refuel quantity switch in the flight compartment, and the pre-selected quantity will then be displayed on the fuel system page of the multifunction display, but also outside at the refuel-defuel panel with the master switch on. When the tank vehicle is connected to the refueling system via the refueling adapter and fuel pressure is applied, the refueling of the wing tank group starts. During the refueling process, the pilot has an opportunity to reselect the required fuel quantity by increasing or decreasing with the refuel quantity switch in the flight compartment, or the pre-selector switch at the refuel-defuel control panel, as long as the pre-selected fuel quantity is not reached. The automatic pressure refueling is terminated when the pre-selected fuel quantity is reached, and the fuel quantity remaining displays for each tank show that the fuel is correctly divided between the left and the right-hand wing tank groups. Manual refueling of the wing tank groups can either be provided by the gravity refueling or pressure refueling. The manual refueling is used as an alternate method if the normal used automatic mode is unserviceable, or the aircraft has to be refilled up to the maximal fuel quantity of about 3,416 kilograms. The pilot can check the remaining fuel quantity in the cockpit on the fuel system page of the multifunction display, the ICUS display, or outside of the aircraft at the refuel-defuel panel if the master switch is on. When the tank vehicle is now connected to the refueling system via the refueling adapter and fuel pressure is applied, refueling can then only be started when the refueling switches at the control panel are switched to the refuel position, and the open lights of the refueling valves illuminate. The manual pressure refueling procedure is terminated when the additional or total fuel load for each wing tank group is achieved, and the refuel-defuel switches are set to the center guarded position. The close lights of the refueling valves illuminate. A pressure relief valve with an outlet duct for each wing tank group is located on the rear spar to protect the applicable wing tank group from deformation if the pressure increases above the specified limit. Should a failure occur during pressure refueling, Then the high pressure acts on the spring-loaded poppet valve to force it into the open position. This allows fuel and the unwanted high pressure to vent overboard through the outlet duct. After relief of the too high amount of fuel, the valve will close again. Normal fuel quantity and fuel flow indication can be monitored on the ICUS and the fuel system page on the MFD. A backup indication is provided on the RMU. Several normal and failure messages for various components and functions are provided on the ICUS and the fuel system page. Failure of a fuel jet pump is indicated by a fail light in the switch light, a jet pump fail message on the ICUS and on the fuel system page. A failure of an electrical boost pump is indicated by a fail light in the switch light, an electrical boost pump fail message on the ICUS and on the fuel system page. A fuel shutoff valve fail message will be displayed on the ICUS and the system page whenever the shutoff valve is not in its commanded position. In case of fuel imbalance of more than 72 kilograms, a blue fuel balance message will illuminate on the ICUS, and in case of a fuel imbalance of more than 95 kilograms, an amber fuel asymmetry message will illuminate. If crossfeed is selected, a blue fuel crossfeed active message will be displayed, and if the fuel crossfeed valve fails to move into the commanded position, the fuel transfer fail message will be displayed. Should the fuel quantity in one of the tank groups fall below 233 kilograms, the amber fuel low VMO message will illuminate on the ICUS, and if the fuel level falls to 77 kilograms, the feed tank low message will illuminate. Dornier 328 hydraulic power consists of a main hydraulic system and the auxiliary system. The system operating conditions are displayed to the flight crew on the electronic indicating, caution, and crew advisory system called ICUS. The main hydraulic system of the Dornier 328 is split into the primary and the secondary hydraulic system. The primary hydraulic system consists of the main reservoir, the AC main pump assembly, the main filter package, the main system accumulator, the pressure sensing valve, the normal brake accumulator with the check valve, the pressure dump and relief valve, the shutoff valve, the double shuttle valve, the outboard pressure line and outboard return line connector, and the main pump switch light. The secondary system consists of the DC standby pump, the standby control pressure switch, the priority valve, the DC standby pump switch, and the priority valve switch. The main hydraulic system pressure is normally generated by an AC electric motor-driven piston pump to supply the following consumer systems: the roll spoiler, the landing gear, the normal and emergency brake system, the trailing edge flaps, the nose wheel steering, and the ground spoiler system, which is optional. The hydraulic power system is controlled via the hydraulic panel and monitored on the multifunction display. The main hydraulic pump is driven by an AC electric motor, which is supplied from the AC electric bus system, powered from the engine-driven AC generator. If the pilot switches on the press-in, press-out switch light, the AC power main pump will be normally powered by the 115 200-volt AC bus 11XP, and the pump starts to operate. The AC pump sucks hydraulic fluid from the main chamber of the reservoir and pressurizes the fluid to the main filter package. Normally, the priority valve is de-energized so that the hydraulic pressure can supply all consumers. The multifunction display, selected to the hydraulic synoptic page, doesn't show any abnormal status. The display shows green lines to all consumers. The DC standby pump switch is normally selected to the auto mode. The automatic standby pump control system is now armed and under the control of the standby control pressure switch and the priority valve relays. If the hydraulic pressure now falls below 1,958 psi, the contact of the standby pump pressure switch will close. The coils of the pump power relay are now energized. The relay will close and the standby pump starts to operate. The contacts of the pressure switch remain closed until the system pressure has increased to 2,886 psi. The standby pump will now stop. This process is repeated even without engines running. The DC pump switch can also be selected on or off by the flight crew's own discretion. The priority valve can be operated in the automatic or manual mode. In the automatic mode, the priority valve is activated if proximity sensor A of the reservoir shows low level and sensor B shows critical level, or proximity sensor A shows low level and the AC pump is off. In both cases, the priority valve would close and the flow of the hydraulic fluid to the normal consumer is isolated and routed to the standby inlet of the roll spoiler double shuttle valve. In this case, the outlet hydraulic line of the roll spoiler system is a special hydraulic return line, which routes the hydraulic fluid directly back into the standby reservoir. In the manual mode, the priority valve can be selected to the permanent on position, the so-called roll selection, or to the disabled position by setting the priority switch to all. In case of a main hydraulic system fail, the auxiliary hydraulic system supplies emergency gear extend assist system or the emergency park brake system. The auxiliary hydraulic system consists of the hand pump assembly, the manual selector valve, the auxiliary reservoir, the emergency park brake accumulator, the pressure dump and relief valve, and the pilot check valve. If the main hydraulic system fails, the landing gear can be extended and the wheel brakes operated by pressure produced by the auxiliary system hand pump. The manual selector valve is already in the landing gear extend assist position when the access cover is opened. The open position of the cover is monitored by the MFD. When the hand pump is operated, fluid is drawn from the reservoir and applied under pressure through the manual selector valve to the gear extend assist circuit. When the landing gear is down and locked, the manual selector valve can be set to the emergency park brake position. The hand pump can now be used to pressurize the emergency park brake accumulator. The MFD indicates when sufficient pressure is available. The hand pump cover can only be closed when the manual selector valve is in the landing gear extend assist position. This ensures that the gear extend assist mode is pre-selected should the auxiliary hydraulic system be required in flight. Ice and rain protection on the airplane is provided by the airfoil de-icing system, which is divided into the pneumatic wing and empennage de-icing system and the electrical elevator and rudder de-icing system. The pneumatic engine intake de-ice system, the probes heating system for the pitot, angle of attack, and true air temperature probes, the electrical windshield and side window heating system, the windshield wiper system, the electrical propeller heating system, and the ice detection system. Airfoil de-icing is provided via inflatable rubber de-ice boots installed on the leading edges of the wing, the vertical and the horizontal stabilizer. Flow control valves are connected to the pneumatic supply system, and when energized, they will supply pressurized air to the de-ice boots. When de-energized, the ejectors of the flow control valves will produce suction, which is applied to the boots to prevent lifting during flight. Control is done by two electronic timers that will energize the flow control valves in sequence, and different operating modes can be selected from the ice protection control panel. Indication is provided via the ice protection system page, and certain messages are displayed on the CAS field. The de-ice boots are controlled from the ice protection control panel, and three different modes can be selected. The single mode, which is controlled by the single mode button and the right-hand controller, the automatic fast and slow mode, which are controlled by the airfoil cycle selector and the left-hand controller. The single mode can be used at the pilot's discretion, and when the ice is estimated to be less than 6 millimeters. When selected, a single cycle of the boots will be activated, and all boots will be fully inflated for about 2 seconds in a given sequence. Boot inflation can be monitored on the ice protection system page. The automatic fast mode is used in heavy icing conditions, meaning an ice buildup of about 10 millimeters within 30 seconds. It will activate de-ice boot cycles with a pause of 18 seconds between cycles. The slow mode is used during normal icing conditions, and it activates de-ice boot cycles with a pause of 138 seconds between cycles. The two automatic modes have priority over the single mode at all times. As soon as the airfoil cycle switch is selected to off, the automatic de-ice cycle will stop and permit immediate use of the single mode. Bleed air supply to the airfoil de-ice system can be controlled via the two bleed switches on the ice protection panel. The operating envelope of the de-ice boots ranges from -40 to +50 degrees Celsius, and when used outside of this range, damage to the system is possible. Normal indication for the airfoil de-icing is provided on the ice protection system page by a blue fast synoptic for the airfoil selector set to fast, a blue slow synoptic for the selector set to slow, and a blue single synoptic for the single mode when activated. A green boot synoptic indicates that the respective leading edge is active and inflated. If a failure indication on the CAS field appears, details can be obtained from the ice protection system page, which will display messages such as fast fail when the fast mode cycle failed, slow fail when the slow mode cycle failed, single fail for a single mode cycle fail, and an amber leading edge synoptics which indicate that the respective leading edge boot has failed. An amber pressure low synoptic and a de-ice pressure low message on the CAS field will be indicated if insufficient de-ice pressure is supplied to the system, and a sensor fail message will be displayed if the de-ice pressure switch has failed. For ice protection, the elevator horns and the rudder horn are electrically heated. Control is done from the left and right horn heater buttons on the ice protection control panel, and temperature control is automatic. Failure indication is provided on the CAS field by a left elevator heat fail message for a left elevator horn or a rudder horn heater failure, and a right elevator heat fail for a right elevator horn heater failure. De-icing on both engine air intakes is provided by 3 pneumatically inflatable de-ice boots installed on intake leading edge, the intake floor, and the intake bypass duct. The engine intake de-ice boots are activated by the left and right engine intake button and controlled by 2 electronic timers. As soon as they are selected on, all 3 intake boots will inflate for 6 seconds, followed by a pause of 54 seconds. This cycle is repeated every 60 seconds. A pressure switch installed in each ejector flow control valve monitors the inflation pressure. The operating envelope of the intake boots is -40 to +55 degrees Celsius, as for all pneumatic boots installed on the Dornier 328. Normal indication for the intake de-ice boots is displayed on the Ice Protection System page. With the intake switches off, the blue off synoptic will be on. And with the intake switches on, the blue on synoptic will be on. With the de-ice boots inflated, the green boot synoptic will be on. If a failure indication on the CAS field appears, details can be obtained from the Ice Protection System page, which will display messages such as an amber fail, which indicates a controller failure, a pressure switch failure or not sufficient de-ice pressure, and an amber boot synoptic, which indicates that the respective intake boots have failed. The probe's heating system provides ice protection for the pitot tubes, the angle of attack vanes, and the true air temperature probe. Each pitot probe has its own single electrical heater, whereas the angle of attack vanes contain 2 heater elements, one at the AOA base and installed inside the vane. Also, the true air temperature probe contains a heating element which functions in the same way as the pitot heating element. Control and indication is done from the ice protection panel. The number 1 button controls the left pitot probe and angle of attack vane. The number 2 button controls the right pitot probe and angle of attack vane. And the standby button controls the standby pitot probe and the true air temperature probe. Failure indication for the probe's heating system is provided on the ice protection panel and on the CAS field for more detailed information. The windshield wiper system is used to remove rain, snow, or slush from the windshields, and 2 conventional wiper blades are used to perform this task. The left and right-hand wiper systems are controlled by the 2 wiper selectors, located on the forward combined panel. They can be operated completely independent from each other during operation on the ground and in flight at airspeeds up to 166 knots. Please note that windshield wipers should not be operated on dry windshields. The windshield wiper blade has a small roller which will lift the wiper clear of the windshield when in the park position to prevent the accumulation of dust and sand which could otherwise scratch the windscreen. To prevent ice buildup and misting, The flight compartment front windshields and side windshields are heated by electrical elements embedded into the windshields. Each windshield has 3 temperature sensors, one for heat regulation, one for over-temperature protection, and one spare sensor. For safety reasons, the system is divided into 2 independent systems, and each windshield is controlled by its own control unit installed in one of the 2 temperature controllers. The number 1 temperature controller contains the control unit for the left front and the right side windshield, and the number 2 controller contains the control unit for the right front and the left side windshield. The windshield heat is activated via the 2 windshield buttons on the ice protection panel. When pushed, the buttons will be dark, and the windshield operating status can be viewed on the ice protection system page. Note that the windshields are also bird-proof, not heated, and therefore windshield heat may be turned off if conditions permit. Failure indication for the windshield heating system is done on the CAS field, and more details can be obtained from the ice protection system page. Propeller ice protection is provided by the propeller de-ice system. Electrically heated rubber de-icer mats are installed in the blade leading edges to prevent or remove ice formation. The left and right-hand systems are completely independent to prevent total loss in case of a failure. Each system contains its own de-ice timer, which controls the de-ice cycles to ensure a balanced de-icing. Operation is controlled from the ice protection panel by the use of the 2 prop selectors, which have the positions off, below -10 degrees Celsius, and above -10 degrees Celsius. Electrical power to the propeller blade is transferred by the brush block, which contains carbon brushes that are pressed against the rotating slip rings mounted on the back side of the propeller hub. Caution! With external AC power connected to the airplane, 115 volts AC is supplied to the propeller slip rings and de-icer mats. Do not touch the slip rings or the propeller de-icer mats if damaged or eroded, as this could be dangerous. A metal oxide varistor is also installed next to the brush block. It protects the aircraft electrical power system in case the propeller is struck by lightning, and in this case routes the reverse current to aircraft ground. Thermostats for each propeller de-ice system are provided to prevent overheating of the propellers in case they are selected to below -10 degrees Celsius at ambient temperatures of +5 degrees. Each timer also incorporates circuitry to monitor the propeller speed. If the speed drops below 50%, heating is disabled to prevent damage to the blade heaters and carbon fiber propeller blades. As long as the propeller selector switch on the ice protection panel is set to off, a blue prop de-ice off message for the respective propeller illuminates on the ice protection system page. When the selector is set to below -10 degrees Celsius, a prop de-ice on message will be displayed on the ICUS and the system page. The timer will then provide power output to the 2 sets of blade heaters, which will alternately cycle with an interval of 25 seconds on, followed by 60 seconds off. If the selector is set to above -10 degrees Celsius, the prop de-ice on message will also be displayed on the ICUS and the system page, but the timer will then provide power output to the 2 sets of blade heaters for alternating cycles with an interval of 7 seconds on, followed by 65 seconds off. Failure messages will be displayed on the CAS field and the ice protection system page. In case of a timer or heater failure, the message left or right prop heat fail will be displayed on the CAS field, and the message Prop De-icer Fail will be displayed on the system page. These messages will also illuminate if the prop speed is below 50%, or if the temperature is above 5 degrees Celsius, with the prop heat set to below -10 degrees. An ice detector probe is installed on the forward right-hand side of the fuselage. The probe vibrates at a certain frequency, and the accumulation of ice will cause a certain change in frequency which is sensed by an electronic circuit, and the crew will be alerted. To allow for continuous operation, the probe also contains a heating element to remove the ice after the crew has been alerted. The ice detector system has a test button, which houses a fail light and a test light, and is located on the ice protection panel. When the test button is pushed, the ice light inside the button, the ice detected message on the CAS field, and on the ice protection system page must come on. When a certain amount of ice builds up on the probe, the ice-detected message on the CAS field and on the ice protection system page will come on. At the same time, the ice caption in the button will illuminate. The ice-detected message will stay on for 5 minutes, whereas the ice signal stays on for about 60 seconds. After that time, the heater is activated to clear the probe from ice. In case of a failure, the fail caption in the button and the ice detector fail message on the CAS field and on the ice protection system page will illuminate. This chapter describes the instrument panels, displays, and controls installed in the aircraft. The main systems are the central display system, instrument and control panels, the recording systems, the central warning system, the central computers, and the automatic data reporting systems. The Primus 2000 Integrated Avionics System architecture contains the following major subsystems: the electronic display system, the attitude and heading reference system, the micro-air data system, the radio altimeter system, the radio communication and navigation system, the flight management system, which is an integral part of the number 1 IAC, and the weather radar system, the fault warning computer, the EFIS display electronic interface, and the auto flight control system, which are integral parts of both IACs. The electronic display system consists of 5 display units: a primary flight display, PFD, and a multifunction display, MFD, for each pilot, and the engine indicating and crew advisory system display, ICAS, the control panels, the display electronic interface, EDS, and the fault warning computer, FWC, installed in each IAC. The data acquisition unit, DAO, and other subsystems such as radios and weather radar connected to it. The fault warning computer is an integral part of the IAC and is primarily responsible to supply engine display data, caution and advisory data on the ICAS, as well as system pages on the MFD. It receives data over the ASCB from the data acquisition units, display controllers, micro-air data computers, and various other systems, and provides outputs for specific horns and cockpit annunciators. The fault warning computer provides test functions for all the subsystems except the Primus 2. The two AHRs installed in the avionic racks are strapped-down all-attitude inertial sensor systems that use interferometric fiber optic gyros. Via the ASCB, they supply aircraft heading, attitude and flight dynamic information to the flight guidance system, weather radar, electronic display system, and other aircraft systems. The two integrated avionic computers, IAC, installed in the avionic racks provide the major avionics computing functions. Each IAC contains a power supply, a cooling fan, and several circuit cards, which are the FMS card, which contains the FMS functions and database and is installed in IAC-1 only, the display processor, the fault warning computer, bus controller and tone generator card, the input-output processor card, auto-flight computer digital and analog cards, which are installed on IAC-1 only, and the radio system bus card. The two IACs are connected to various buses and components that communicate with the IACs. In case of a single IAC failure, the remaining IAC is able to provide the required data to the aircraft systems. The MFD bezel controller provides access to several display menus and submenus. It consists of 5 bezel control buttons: the rotary knob, which is used to select certain values, the menu select button, and the bezel display. By the use of the bezel control buttons, various menus, submenus, and MFD formats can be selected. The Menu Select button is used to return to the previous page, or to cycle between the main menus on the MFD. From the main menu 1, the Display menu, the Radar menu, the FMS menu, and the MFD format can be selected with the bezel control buttons. From the main menu 2, the Test menu for various system tests, engine exceedance data, which is recorded if certain engine parameters are exceeded, or the Ground Maintenance menu, which is for maintenance purposes only, can be called up. By selecting the Captain or First Officer Systems button on the ICUS, the MFD will display the aircraft system synoptic pages. By the use of the bezel control buttons, certain aircraft systems can be selected, and you can also return to the main menu via the Menu Select button. The reversion panel contains the switches for the multifunction display, the data acquisition unit channels, the attitude and heading reference source, the air data computer source, and the symbol generator. In case of a display unit failure, the MFD reversion switch allows the selection of the MFD as the display unit for the ICUS and the on-side primary flight display. Note that some functions will not be operable if MFD reversion mode has been selected. The Dow channel selector is used in case of a single Dow channel failure. Selection of the switch will cause the respective channel B to supply data to each IAC and restore indication. The Attitude Heading Source Selector can be used in case of a single AHARS failure. Selecting the switch will cause all displays to indicate information from the selected source. The selected source will also be displayed in the PFD source annunciation display. The Air Data Source Selector can be used in case of a full or partial Air Data computer failure. Selecting the switch will cause all displays to indicate information supplied from the selected source. The selected source will also be displayed in the PFD source annunciation display. The Symbol Generator Reversion switch selects which IAC symbol generator supplies information to the display units. When selected, an amber symbol generator message will show up on all MFDs and PFDs. A failure of the number 1 symbol generator is recognized by the following displays: by a red X on the number 1 PFD, on the number 1 MFD, the ICUS, or by a combination of all three displays. If this happens, the symbol generator reversion switch has to be selected from normal to the number 2 position. This will cause all display units to indicate number 2 symbol generator information, and an amber symbol generator number 2 message is displayed on all PFDs and MFDs. In case of a number 2 symbol generator failure, a red X will appear on the number 2 MFD, the number 2 PFD, or on both display units. In this case, the reversion control switch has to be selected from the normal to the number 1 position. This will cause all displays to indicate number 1 symbol generator information, and an amber symbol generator number 1 message will be displayed. In case of a multiple display unit failure, either Radio Management Unit, RMU, can be used as a backup navigation display. Indication will be displayed in an HSI ARC format and contain information about VOR ILS navigation course, DME distance, VOR and ADF bearing pointers, selected VOR and ADF frequency, and the marker beacon. Failure indication on the RMU for various systems is provided in a way similar to the main displays. The Dornier 328 cockpit has 2 independent multifunction displays, MFDs, that are capable of providing the following display formats: the ARC mode, the compass rose mode, the plan mode, and the airplane system's display. Certain symbology provided on the MFD is available in all navigation modes. These symbols are located in the lower left and right-hand corner and represent information such as static air temperature and true airspeed, which are provided by the air data computer, the ground speed, which is supplied by the FMS, the weather radar mode annunciations, the radar tilt angle with the up and down arrow, and the target alert, which turns amber and flashes when activated, the variable gain, which displays the value for radar gain if selected, the wind display, which shows the direction and the velocity in knots, the navigation waypoint data, which displays the distance to and the identifier of the selected station, the flight plan data with its various symbols, the estimated en route or time to go, the vertical profile which is not available in the rows mode. The ARC format is the power-up default display on the MFD and has the following unique symbology. The heading source annunciation, which is the same source that drives the PFD. The airplane symbol, which provides a visual image of the airplane's position. The heading select display and bug, with an arrow that will come into view if the bug is selected off-scale. The drift bug, which represents the actual track above the ground, and therefore shows the drift angle. The range rings, which aid in determining the distance of weather radar returns and flight plan parameters. The lateral deviation display, which shows course deviation to the left and right in digital form. The cursor, which displays a point selected and designated by the pilot. The level-off predictor, which represents the approximate distance required to reach a selected flight level. And the weather information from the radar. This information is only displayed in the ARC format. The plan mode is a north-oriented representation of the active flight plan, with the airplane symbol at present position at all times and moving about the display. A range ring is displayed to aid in determining the position within the active flight plan. In the compass rose format, the MFD displays the following unique compass rose data. The 360-degree heading display, which rotates around the stationary airplane symbol. The heading bug and digital readout. The course deviation bar and course pointer with digital readout, which can either display short or long-range navigation source data. The drift bug, which represents the aircraft drift angle. The nav source annunciation, which is the same as the nav source displayed on the PFD. The to from indication. The bearing pointer and annunciation. The vertical navigation scale. The distance display and the navigation preview mode, which gives the crew the possibility to preview other navigation sources. Failures on the MFD navigational display will be shown as follows. In case of an AHARS failure, the bearing pointer's course deviation pointer and bar, the wind display, and the to from indicator will be removed from the display. In addition, a red heading fail message will be displayed at the lubber line, and the digital readout will be replaced by amber dashes. A DME or FMS distance signal failure will be indicated by amber dashes instead of the numbers. In case of a course deviation indicator failure, the deviation bar will be removed, and a red X is drawn through the deviation dots. Failure of the course select signal is indicated by removal of the course pointer and displaying amber dashes in the digital display. In case of vertical radio navigation source failure, the deviation pointer will be removed and a red glide slope message is displayed. An air data computer failure will be indicated by displaying amber dashes instead of the digital values for true airspeed and static air temperature. And a weather radar failure will be shown by a weather radar fail message. In the airplane system mode, the MFD shows various airplane system synoptic block diagrams, such as the flight control page, the hydraulic page, the engine page, the fuel page, the electric page, the ECS page, the ice protection page, the CPCS oxygen page, the doors page, the system maintenance page, and the sensor data page. Two chronometers are installed on the glare shield panel, which indicate local time, LT, Coordinated Universal Time, UTC, Flight Time, Stopwatch, SW, Down Counter, DC, and Date. They are controlled by 3 buttons and are normally powered by 28 volts DC. An internal lithium battery is used to keep alive power, and a low battery signal indicates the need for battery replacement. The number 1 is the master chronometer and supplies UTC and date to the 2 IACs and to the slave chronometer. The aircraft recording system consists of the Flight Data Recorder, FDR, and Data Loader System. The Flight Data Recorder is crash and fire resistant and operates automatically during flight or with one engine running. An underwater locating beacon, ULB, is also installed on the FDR. It starts to transmit when the ULB is immersed in either fresh or salt water. Mounted next to the FDR is a G-switch, which will automatically interrupt the 115-volt AC power supply if the acceleration forces exceed 4G. In case of an FDR failure, or if it requires maintenance, respective messages are displayed on the ICUS. The data loader system is interconnected with IAC 1 and 2. It is used for data exchange such as engine trend and IMT fault data download, as well as navigation data transfer to the FMS database. It consists of the 3.5-inch floppy disk drive and various control buttons mounted in the observer panel. The ICUS bezel controller provides access to the main and reference data display menu selections. It consists of 5 bezel control buttons, the rotary knob, which is used to select certain values, the menu select button, and the bezel display. By the use of the bezel control buttons, various menus can be selected. The Menu Select button is used to return to the previous page. By pushing the Ref Data button, the Reference Data menu is entered, which allows selection of the Takeoff Data menu, the Climb Data menu, the Cruise Data menu, the Landing Data menu, and the Single Engine Data menu. By pushing the Copy button, the Copy submenu comes into view, which allows the pilot to select certain cross-side MFD formats on the MFD display. Upon execution of the Copy function, the ICUS menu will return to Main, and when the Menu Select button is pushed, the Copy function will be cancelled. By pressing the AHARS button, the AHARS 1 and 2 submenu is displayed, which allows selection between the AHARS Normal and DG mode. Selecting DG allows the pilot to manually set the displayed heading by the use of the Set knob. The electronic indicating caution and advisory system consists of the following indicating components: the display unit and bezel buttons, the red warning panel, the master warning and master caution button, the standby engine and CAS display on either radio management unit. The Electronic Indicating Caution and Advisory System display, ICAS, replaces the majority of the traditional engine and indicating gauges. It can be divided into the following 5 areas: the primary engine display, the crew alerting system field, the cabin altitude display, the trim flaps display, and the menu selection display. The engine display shows information about engine torque, propeller speed, interstage turbine temperature, high-pressure compressor speed, oil temperature, oil pressure, fuel flow, and fuel quantity. The torque indication has a digital and analog display with a white range of 0 to 100.5%, a no pop-out range of 100.5 to 103%. The pointer, digits, and scale will pop up red if within this range for more than 5 seconds, and a red range of 103 to 120%. At torque readings above this range, the pointer will remain at 120%, and the digital reading will increase up to 161%. A green torque bug is provided and can be set with the ICAS bezel control knob with reference data selected. A flight phase annunciation for climb, cruise, landing, and single engine is provided and also depends on selected reference data. The propeller display has 2 white ranges, one from 0 to 27.1%, and one from 69.2 to 102.7%, an amber range from 26.9 to 69.4%, and a red pop-up display for the range between 102.5 and 110% for the pointer, whereas the digital display increases up to 200%. 2 sync bugs are provided, one in the range from 79.23 to 82.30%, and one in the range from 83.08 to 86.13%. When the prop speed approaches the bug, it will turn blue, indicating the armed status. A green indication shows that the synchro phase is armed on both sides. If the synchro phase is on, the blue sync caption will illuminate. The beta annunciation indicates that the propellers operate in the negative or 0 thrust region. The interstage turbine temperature display has a white range of 0 to 801 degrees Celsius, with a red tick mark at 800 degrees. A red pop-out range is provided for indication from 800 to 850 degrees, and the digital readout can increase up to 1200 degrees. However, the pointer stops at 850 degrees. For engine starting, an amber range between 800 and 950 degrees is provided with tick marks at 800, 850, and 950 degrees. If the temperature remains in the range between 850 to 950 degrees for more than 5 seconds, the whole segment will turn red. And if the temperature remains in the range between 800 and 850 degrees for more than 20 seconds, the entire segment will also turn red. The ignition annunciator will come on whenever the respective ignition is turned on. The high-pressure turbine speed display, NH, has an amber range of 0 to 64%, with tick marks at 0 and 64%, a white range between 64 and 102.9%, with a tick mark at 102.7%, and a red pop-up range between 102.7 and 110%. Further, an NL annunciator will illuminate if a low-pressure turbine speed is not maintained within its normal limits. It will be amber for underspeed and red for overspeed. The normally white horizontal scale of the oil pressure display is augmented by a red field in the range between 0 and 40.5 psi, and an amber range between 40 and 55.5 psi. The normally white horizontal scale of the oil temperature display is augmented by an amber field in the range between -40 to 45 degrees and 115 to 145.5 degrees Celsius, which will turn red when operating in this range for more than 20 minutes, and the red range from 145 to 150 degrees. The fuel flow indication shows current fuel flow, and the fuel quantity indication shows usable fuel remaining. The display turns amber if the VMO is limited due to low fuel quantity, the feeder tank quantity is low, or calculated fuel quantity is displayed. A Dow channel failure or engine sensor failure is indicated by a boxed question mark instead of the pointer, amber dashes instead of the digital readout, and an engine miscompare message on the ICUS. The cabin altitude display shows the cabin pressure altitude in feet and the current cabin rate of change in feet per minute. The trim flaps display shows position of the aileron trim, the rudder trim, the elevator trim, and flaps position. In case trim flaps display shows position of the aileron trim, the rudder trim, the elevator trim, and flaps position. In case of a flap asymmetry, or if the flaps are in disagreement with the selected takeoff data, the indication will turn amber. The crew alerting system consists of the CAS field, the red warning panel, and the master warning caution button. If a warning illuminates on the red warning panel, a triple chime will be audible, and the master warning will flash. When the master warning is pushed, the light will be extinguished. If a caution message illuminates on the CAS field, a single chime will be audible, and the master caution will flash. If the switch is pushed, the light will extinguish, and the message on the CAS field will stop flashing. Some warning and caution messages activate the system display auto call-up function on the ICUS bezel menu. Blue status messages will always appear below the caution message stack and flash for 5 seconds. Thereafter, indication will be steady with no pilot action required. The landing gear of the Dornier 328 consists of the landing gear system, the wheel and brake system, with the anti-skid system, and the nose wheel steering system. The main gear assembly is a twin-wheel trailing arm gear with an oleo-pneumatic shock absorber. The main gear is locked in the down position by a side strut assembly, which is connected between the fuselage and the main gear leg, and incorporates an over-center downlock mechanism and a downlock release actuator. The main gear door assembly consists of an upper and middle foldable door and a lower main door. The gear doors are actuated by a mechanical linkage when the gear retracts and extends. The nose landing gear assembly is a twin-wheel, hydraulically steered gear with an oleo-pneumatic shock strut. The nose gear is locked in the down position by a downlock strut, which incorporates an over-center downlock mechanism provided by a downlock spring and a downlock release actuator. The nose gear is pivot mounted between the left and right walls of the nose gear bay and is retracted forward by hydraulic power. The nose gear doors consists of left and right forward and left and right rear doors. The gear doors are actuated by a mechanical linkage when the gear retracts and extends. The landing gear is extended and retracted by hydraulic power supplied by the main hydraulic system. By moving the landing gear control lever to the up position, an electrical signal is sent to the proximity sensor electronic unit, which will then check for weight of wheels and landing gear condition. It will then provide an electrical signal to the landing gear selector valve, which will move into its up position and provide hydraulic pressure to all three landing gear units. By the use of a restrictor in the retraction extension actuators, hydraulic pressure is first routed to the down lock release actuator to break the over center of the lock actuator, which initiates the retraction process, and then to the landing gear actuator to complete the landing gear retraction. As soon as the landing gear is up and the up lock hook has engaged, the proximity sensor electronic unit will remove the electrical signal from the landing gear selector valve, which will then move into its neutral position and remove all hydraulic pressure from the landing gear system. By moving the landing gear control lever to the down position, an electrical signal is sent to the proximity sensor electronic unit, which will then check for landing gear condition. It will then provide an electrical signal to the landing gear selector valve, which will then move into its down position and provide hydraulic pressure to all three landing gear units. By the use of a restrictor in the retraction extension actuators, hydraulic pressure is first routed to the up lock hook actuator to unlock the gears of the up lock hook, which initiates the extension process, and then to the landing gear actuator to complete the landing gear extension. As soon as the landing gear is down, the main gear side struts and the nose gear lock strut are mechanically driven into their over-center downlock position. The proximity sensor electronic unit will remove the electrical signal from the landing gear selector valve, which then will move into its neutral position and remove all hydraulic pressure from the landing gear system. If an electrical or hydraulic fault occurs, the landing gear has to be extended by an alternate method. The emergency extension system does not require electrical power, and it is supplied with hydraulic power from the auxiliary hydraulic system. When the hand pump cover at the aft end of the center pedestal is opened, the emergency extension valve and the bypass valve are actuated by mechanical linkages. The manual selector valve is in its initial position, gear. Actuating the hand pump handle generates hydraulic pressure, which is applied to the emergency gear extension line through the emergency extension valve. When sufficient hydraulic pressure has built up, the emergency hydraulic cylinder of each gear up-lock hook will now unlock the gear. The gear legs drop out by gravity. The force of gravity, assisted by aerodynamic forces, drives the nose gear downlock strut into its over-center downlock position. The main gears will not lock down without assistance, and further hydraulic pressure must be generated by the hand pump. This pressure is applied to the main gear downlock assist actuators and provides the power to drive the main gear side struts into their over-center downlock position. If an electrical power failure is the reason for the failure of the normal extension system, there will be no indication when the gears are locked down. The only indication will be the possible audible indication of the downlock snapping into the over-center position. In this case, the pump should be operated until the pressure felt at the pump handle increases noticeably. The landing gear control lever is installed in the center right-hand side of the instrument panel. The unit consists of 3 green and 3 red gear position lights, a gear selector lever, a red gear warning light in the selector lever, a solenoid-operated lever lock, a lever lock release knob, and a test button. 3 green lights indicate gear down and locked, and 3 red lights indicate gear in transit or not locked in the selected position. All these lights are extinguished when the gear is up and locked. A non-mutable aural warning combined with a red flashing light in the landing gear control lever occurs if the landing gear is not down and locked, and both power levers are retarded to a point slightly above flight idle, and the height indicated from the radio altimeter is less than 400 feet. The lever lock solenoid prevents the lever from being moved into the up position until all 3 gear legs have left the ground. A red knob marked down lock release is located to the lower left of the gear lever. The push to release knob allows the flight crew to manually override the lever lock solenoid at their discretion. The test button is used to test the gear warning light and the aural warning. The caution and status messages are displayed on the crew alerting system field of the ICUS display and on the hydraulic synoptic page on the captain's and first officer's multifunction display. On the ICUS, the following landing gear messages can be displayed. The gear uplock fail, 1 or more gear uplocks detected by the PSEU while all gears are down and locked. The message proximity system replaces the message proximity hydraulic single if more than one proximity sensor has failed. On the multifunction display, the following landing gear messages can be displayed. Proximity weight on wheel fail illuminates when a failure in the weight on wheels proximity sensor is detected. Proximity lock fail illuminates when one of the gear lock proximity sensors has failed. Proximity system fail illuminates when a failure in the proximity sensor system is detected. The emergency landing gear indication followed by a solid synoptic line when the auxiliary system is activated, which is normally dashed. And the landing gear white indication during normal operation supplied by the main hydraulic system indicated by a solid green line. Each landing gear is equipped with 2 wheels, and each wheel is equipped with a hydraulically operated multi-disc brake. Under normal operating conditions, the wheel brakes are controlled by the normal brake system, which is controlled via the rudder pedals. In case of a normal brake system failure, an emergency brake system, controlled via a handle in the flight compartment, is available. This emergency brake system is also used as a parking brake. The brakes are actuated by applying toe pressure to the rudder pedals. This ensures that hydraulic fluid in the associated brake master cylinder is displaced. The amount of displacement is proportional to the force and stroke of the pedal movement. The displaced fluid is applied through the hydraulic line to the brake metering unit, which includes the metering valve. This allows metered pressure from the main hydraulic system via the anti-skid valve and shuttle valve to the brake unit, proportional to the metering valve opening. Differential braking is provided to control the aircraft on the ground with inoperative nose wheel steering. When the emergency park brake handle is pulled, the brake valve opens. The valve allows hydraulic pressure from the emergency park brake accumulator, which is supplied by the main as well as the auxiliary hydraulic system through the shuttle valve manifold to the brake units. The amount of brake application is proportional to the force and stroke applied to the handle. The emergency park brake pressure switch is connected to the pressure line, and the switch shows brake on or brake off status signals to the ICUS. The caution and status messages are displayed on the crew alerting system field of the ICUS display and on the hydraulic synoptic page on the captain's and first officer's multifunction display. The following brake system messages can be displayed. The brake temperature high, indicating that the temperature of the associated brake stack is above the limit. The brake temperature inoperative, showing that one or more brake temperature signals are invalid. The park brake on or off status message. When the aircraft is in the takeoff configuration and the takeoff warning is triggered, the brake on status message changes over to a caution message. On the multifunction display, the following brake system messages can be displayed. The normal brake with the pressure indication of the main system and the park brake accumulator. The trend vector is a magenta strip that varies in size and position as the brake temperature increases. The length of the strip shows the brake temperature trend in degrees Celsius per minute. The normal brake system is equipped with an anti-skid facility. 2 anti-skid valves are installed on the brake metering unit. One valve modulates the hydraulic pressure to both left-hand wheel brakes, and the other the pressure to both right-hand wheel brakes. The valves are electrically controlled by an anti-skid control unit, which receives signals from a wheel speed sensor on each main wheel. The control unit will detect if one of the wheels decelerates faster than the other 3 wheels, and sends a pressure dump signal to the associated anti-skid valve. This releases the pressure to the brake pair on the corresponding gear leg. The control unit also receives signals from various landing gear sensors which signal the status of the gear. The anti-skid subsystem provides touchdown and locked wheel protection to prevent flatting or bursting tires on touchdown and during the landing run. The anti-skid system can be disabled at the pilot's discretion by pressing the anti-skid switch. Monitoring and controlling the anti-skid system is accomplished by the anti-skid control button, the ICUS display, and the multifunction display. The anti-skid system can be manually switched on or off. The caution and status messages are displayed on the ICUS and the multifunction display. On the ICUS, the following anti-skid system messages can be displayed. The anti-skid fail at an anti-skid system failure when at least one main landing gear is down and locked, and the anti-skid inoperative message if the system is switched off or at a total loss of the electrical power with no anti-skid system failure. On the multifunction display, the following anti-skid system messages can be displayed. The anti-skid fail at an anti-skid system failure, and the anti-skid inoperative message if the system is switched off. The aircraft is equipped with a nose wheel steering system, which is powered from the main hydraulic system. The steering is controlled by commands from either the rudder pedals or from a hand control unit, the tiller. The maximum deflection via the rudder pedals amounts to plus or minus 10 degrees, and the tiller provides a maximum nose wheel deflection of plus or minus 60 degrees. When the condition levers of both engines are set to high taxi, and one condition lever is advanced, the steering command signals from the hand control unit are inhibited. The command signals from the rudder pedals are always available but can be disabled by pressing and holding the pedal disconnect button on the tiller. This is necessary, for example, at strong wind conditions, when rudder deflections could occur during a turn, which would cause unwanted nose wheel steering deflections. The nose wheel system is also equipped with an anti-shimming device, provided by two anti-cavitation valves in conjunction with an accumulator, and the nose wheel is automatically centered when the nose gear extends or retracts by a cam follower type centering mechanism formed by two cams. The steering electronic control unit sends a command signal to the hydraulic control manifold to center the nose wheels if one of the two weight-on-wheel sensors supply the ECU with a weight-off-wheel signal via the PSEU. The nose wheel steering is selected on or off by the nose wheel steering button. The controlling and monitoring of the nose wheel steering system is provided by the nose wheel steering mode switch, the ICUS display, and the multifunction display. The nose wheel steering button upper field shows the identification field, which is always on. The lower field monitors the on or off position. The caution and status messages are displayed on the ICUS and the multifunction display. On the ICUS, the following nose wheel steering system messages can be displayed. The nose wheel steering bypass fail, if a failure in the control manifold occurs and the bypass valve is activated, or the nose wheel steering power supply is switched off. The nose wheel steering power up fail, if the electronic control unit has an internal fault. The nose wheel steering fail, if the ECU detects a failure in the steering system or the main hydraulic pressure is low. And the nose wheel steering inoperative status message when the steering is switched off manually by the pilot. On the multifunction display, the following nose wheel steering system messages can be displayed. The proximity bypass fail, when the proximity sensor of the nose wheel steering bypass valve has failed. The nose wheel steering fail, if the ECU detects a failure in the steering system or the main hydraulic pressure is low. The nose wheel steering bypass fail, if the steering bypass system has failed. And the nose wheel steering inoperative status message when the steering is switched off manually by the pilot. The landing lights are installed in the left and right-hand main landing gear fairings. The lights are controlled by two landing light switches, which are located on the external light section on the light control panel. Two taxi lights are installed on the nose landing gear strut. The taxi lights are controlled by a taxi light switch, located on the external light section on the light's control panel, and they can only be activated when the landing gear is extended. When the landing gear is retracted, the taxi lights will be switched off automatically, regardless of the taxi light switch position. The identification lighting consists of a red flashing anti-collision light, which is located in the lower fuselage and controlled by the anti-collision light switch. The two strobe lights located on each wingtip, which are controlled by the strobe light switch, and the navigation lights installed on each wingtip and the tail, which are controlled by the nav light switch located on the external light section of the light control panel. The miscellaneous lighting consists of the wing inspection lights and the air stair door lights. The wing inspection lights are located on the left and right-hand side of the forward fuselage and illuminate the wing leading edges and the engine intakes. They are controlled by the wing inspection light switch on the external light section of the light control panel. The air stair door lights are controlled by the stair light switch located on the flight attendant panel. Aircraft lighting system is divided into the interior lighting, the exterior lighting, which is subdivided into the identification lighting and the miscellaneous lighting, and the emergency lighting system, which provides illumination in case of a failure of the primary airplane electrical power system. Control of the lighting is done via rheostats and buttons located on the light's control panel in the flight compartment overhead panel and on the flight attendant control panel. A dome light in the flight compartment ceiling provides general illumination of the flight compartment. The dome light is controlled by a switch installed on the light control panel that can either be set to on, off, or timer, which will cause the light to extinguish automatically after about 3 minutes. A pedestal light in the overhead console illuminates the center pedestal. The light intensity can be regulated by a knob located next to the light. Reading lights are installed in the flight compartment ceiling above each pilot. The lights can be pivoted, and the light intensity can be regulated as required. In addition, console lights are installed in the lining above the captain's and first officer's side console. The control and dimming system allows for testing of the annunciator lights, warning lights, instrument and panel lights. For illumination of the passenger compartment, 3 lighting strips with a total of 20 individual fluorescent light tubes are installed in the cabin ceiling. They are controlled from the flight attendant panel by the use of 2 cabin lighting control switches. For initial and basic lighting of the cabin, boarding lights in the form of 5 dome lights are installed in the cabin ceiling. They are controlled by the boarding light switch on the flight attendant panel. When the switch is selected to timer, the boarding lights will automatically extinguish after about 3 minutes. Reading lights for each passenger are installed in the passenger service units above the passenger seats. The right-hand PSUs are equipped with 2 reading lights, and the left-hand PSUs are equipped with 1 reading light. The reading lights are normally operated by the reading light button on each PSU, and the complete system can be controlled and tested by the reading light switches on the flight attendant panel. Note that if the reading lights are selected to off on the flight attendant panel, the no smoking and the fasten seatbelt signs on the PSUs will also be turned off. Lavatory lights illuminate the inside of the lavatory compartment. Basic lighting is provided by a fluorescent light tube operated by the cabin lighting system. The light above the wash basin illuminates when the lavatory door is locked, and the dome light is operated with the boarding lights. For illumination of the galley area, a light is installed in the passenger compartment ceiling. This galley light is operated by the galley light switch, located on the control panel on top of the galley. The passenger call system enables the passengers to call the flight attendant. A button is installed on each PSU, and when the button is pressed, the call left hand, right hand, or call toilet light at the flight attendant panel will illuminate, and a chime will sound which informs the flight attendant that a button has been pressed. Each PSU contains a no smoking and a fasten seatbelt sign, which are displayed as symbols. Symbols are also provided on the passenger information panel above the flight attendant seat. These lights are controlled with 3 position switches located on the lights control panel, and when these switches are selected to auto, the lights will automatically illuminate when the landing gear extends. The no smoking light will also automatically illuminate if the oxygen masks drop out. Further, a return to seat sign in the toilet will illuminate when the passenger information signs are activated. In addition, a toilet occupied sign is installed on the passenger information panel, and it illuminates when the lavatory is locked. The cargo compartment is illuminated by two lights installed in the cargo compartment ceiling. The lights are controlled by a 3-position switch installed inside the cargo compartment, and when the switch is selected to timer, the lights will automatically extinguish after about 3 minutes. In case the primary aircraft electrical power system fails, the emergency lighting system provides illumination of the cabin and cockpit. It consists of lighting for the emergency exits, the floor escape path lighting, and the external emergency lighting. The emergency lights can be controlled by the emergency lights switch, located on the lights control panel, which provides a manual on and off selection, and by the emergency lights switch on the cabin attendant panel, which provides a manual on selection only. Electrical power for the emergency lights is provided by 4 nickel-cadmium power packs, which are normally kept charged by the aircraft electrical power system. If the aircraft electrical system fails and the emergency light switch in the cockpit is set to arm, the power packs will automatically supply all emergency lights for a duration of up to 10 minutes. The navigation system consists of the electronic display system, the flight guidance and flight management system installed in the IAC, the air data system, the integrated radio system, the weather radar system, the radio altimeter system, the attitude and heading reference system or the optional inertial reference system, the ground proximity warning system, GPWS, the traffic collision and avoidance system, TCAS, and the global positioning system, GPS. The Integrated Flight Control System, IFCS, provides fail-passive flight director guidance, autopilot, yaw damper, and trim functions. The signals are processed and generated by the Flight Guidance Processor, installed in the number 1 IAC. The Avionics Standard Communication Buses, ASCB, provide serial communication between the systems and subsystems. 2 main buses are provided that interconnect all units. For increased system redundancy, 2 backup buses are provided that interconnect units on their sides only. The IAC receives information from the guidance controller and the displays for the required heading course and source logic via private lines. Further, it receives information from various navigation systems via the radio service buses. It will then process all information and supply the electronic display system with the correct attitude, air data, and navigation information. The micro air data computer receives air temperature and pressure information from the true air temperature probe, the pitot probes, and the static port for computing of the standard air data functions. The micro air data computer receives inputs from the total pressure sensor, the static pressure sensor, the temperature sensor, the weight on wheels sensors, barometric corrections, and the fault warning computers. It then provides outputs to the ECS system, the oxygen system, the de-icing system, and the flight control system, as well as to the various systems for indication, recording, and navigation. The micro-air data computers automatically perform the static source error corrections for the number 1 and number 2 static source, depending on airspeed and flap position. Air data information for airspeed, altitude, and air temperature is displayed on the PFD and MFD. The standby air data system is a backup system in case of a failure of both micro-air data computers. It consists of the standby pitot and static ports and the standby air data instruments. The standby altimeter airspeed indicator has two separate mechanisms, one for altitude and one for airspeed. One revolution of the altimeter pointer represents 1,000 feet, and the altimeter has a range of -1,000 to +50,000 feet. The altimeter has a dual baroset counter with the range of 948 to 1,050 millibar and 28.0 to 30.99 inches of mercury. The airspeed is displayed on a revolving drum and has a range of 60 to 450 knots. The standby altimeter airspeed indicator receives power from the emergency power bus for lighting and for driving the internal vibrator. The standby horizon is a self-contained unit with its own emergency power supply, which will supply 24 volts DC to the unit in case of a complete power failure in flight. During normal operation, the batteries of the emergency power supply are charged by the airplane main power supply. The standby compass is a self-contained magnetic compass which provides information about aircraft magnetic heading. 5 volts DC from the emergency power bus via the dim box is supplied to the unit for integral lighting. The aircraft is equipped with a number 1 radar altimeter and an optional number 2 radar altimeter system. The antennas for the number 1 and the optional number 2 radar altimeter are located on the rear fuselage. The radar altimeter measures the height above the terrain and supplies this information to the electronic display system. The radar altitude is indicated on the PFD. Above 200 feet, it has a resolution of 10 feet. And below 200 feet, the resolution is reduced to 5 feet. At altitudes above 1,500 feet, the resolution is reduced to 50 feet. And at a radar altitude of 2,500 feet, no indication will be shown. With decision height selected, the radar altitude will start to flash if the altitude is within 50 feet of the selected decision height, and it will turn amber and stop flashing if at or below the decision height. A self-test for the radar altimeter can be selected via the MFD test menu. If selected, the radar altimeter will display an altitude of 100 feet. The Traffic Alert and Collision Avoidance System, TCAS, interrogates ATC transponders to detect aircraft in the vicinity. The TCAS antennas are mounted on the top and bottom of the aircraft. The TCAS computer receives inputs from various aircraft system components and communicates with TCAS computers aboard other aircraft. It will then compute bearing, range, and closure rate of other aircraft and provide the pilot with a visual and aural warning if applicable. TCAS indication is provided on the PFD vertical speed scale and on the MFD. Certain conditions will cause the TCAS buttons on both sides of the instrument panel to illuminate. Pushing one of the TCAS buttons will cause the TCAS MFD format to appear on that side. A Ground Proximity Warning System, GPWS, is installed in the right-hand avionic rack. The system monitors the aircraft flight profile and provides visual and aural warnings in case the aircraft enters a critical flight path. A glide slope switch in the flight compartment is provided to cancel the glide slope warning. A flaps override button is provided to inhibit the too low flap warning. And an approach button is provided to select the steep approach mode. The GPWS is connected to the digital buses and receives inputs from various aircraft system components. The aural low-level warning output is connected to both audio panels, and the high-level warning is directly connected to the third loudspeaker installed in the cockpit. Two different tests for the GPWS are provided on the MFD test page. The short test is performed by pushing the test button momentarily, and the long test is performed by pushing the test button for about 3 seconds.
Pull up. Think rate. Pull up. Terrain. Pull up. Don't think. Too low. Terrain. Too low. Gear. Too low. Flaps. Too low. Terrain. Glide slope. Minimums. Minimums.
Several different warning modes are provided. The following sequences will show their warning envelopes and applicable aural warnings.
Think rate. Pull up. Think rate. Pull up. Terrain. Terrain. Pull up. Terrain. Terrain. Pull up. Terrain. Terrain. Don't think. Too low. Terrain. 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 Too low. Terrain Too low. Gear. Too low. Terrain. north left. 2 north terrain. Glide slope. Glide slope. Glide slope. Minimums. Minimums.
The aircraft is equipped with 2 independent VHF navigation systems, designated as VHF NAV-1 and VHF NAV-2, which are part of the 2 integrated navigation units installed in the left and right avionic rack. The systems are controlled by the 2 RMUs and the clearance delivery head installed in the cockpit. Two wideband VOR localizer antennas are located on the left and right-hand side of the vertical stabilizer, and a glide slope antenna is mounted inside the radome. The marker antenna is mounted on the lower side of the fuselage. The VOR localizer frequencies are selected by using the RMUs, and the number 1 system can also be controlled by the clearance delivery head. VHF navigation information can be displayed on the PFD, MFD, and the RMU. VHF nav audio signals are also provided to the audio panels for identification and communication purposes. Marker beacon information is also indicated on the PFD. The marker beacon receiver cannot be controlled via the RMU, but the marker volume and sensitivity can be adjusted on the audio control panel. The aircraft is standard equipped with 1 automatic direction finder ADF, which is an integral part of the number 1 INU installed in the left-hand avionic rack. An optional ADF2 can be installed in the number 2 INU. The ADF antenna is a single housing loop sense antenna and mounted on the lower side of the fuselage. The ADF frequency and operating mode is controlled from the RMUs, and indication is displayed on the PFDs and on the MFDs. ADF audio signals are supplied to the audio panels for identification purposes. The aircraft is standard equipped with 1 air traffic control transponder system, ATC, which is an integral part of the number 1 INU installed in the left-hand avionic rack. An optional ATC number 2 transponder can be installed in the number 2 INU. The ATC antennas are installed in the forward top and bottom sections of the fuselage. The transponder system is Mode S capable. The ATC transponder is controlled from the RMUs. The different operating modes are standby, on where the transponder replies to mode A and S interrogations without transmitting altitude information, and alt, where the transponder replies to mode A, C, and S interrogations and does transmit altitude information. The aircraft is standard equipped with one DME system installed in the number 1 INU. An optional number 2 DME system can be installed in the number 2 INU. The DME channel selection is controlled on the RMU and is normally tuned together with the VOR localizer channels. However, independent selection is possible, but DME information for only one station can be displayed at the PFD and MFD for each installed DME. The aircraft can be equipped with an optional GPS receiver. The GPS provides outputs to the flight management system for precision position computation and long-range navigation. The GPS operating status can be viewed on the FMS. The GPS antenna is located on the upper side of the fuselage. The purpose of the oxygen system is to provide the crew and the passengers with oxygen in the event of a pressure loss or in case of smoke or toxic fumes in the cockpit. We divide between the crew oxygen system, the passenger oxygen system, the portable oxygen system, and the oxygen indicating system. Storage for the crew and passenger oxygen system is provided by a 1,415, 2,180, or 3,256-liter oxygen cylinder installed in the aft right-hand main landing gear fairing. For safety reasons, the bottle is mounted outside of the pressurized area, and a shutoff valve is installed on the cylinder to isolate the system when required. Also installed inside the oxygen compartment is a pressure gauge, an oxygen fill port for recharging, and an overboard discharge port, which allows the oxygen to escape if the pressure exceeds 2,775 psi at 21 degrees Celsius. Should this happen, the green overboard discharge indicator disc will be missing. With the shutoff valve on the oxygen cylinder open, flow is provided to the pressure regulator, which reduces pressure to 70 psi and provides low-pressure oxygen to the demand regulators of the 3 crew oxygen masks. Oxygen is also provided to the passenger system solenoid valves, the first aid outlets which can be used to connect a maximum of 4 first aid masks, and the separation valve in the cockpit. Should a leak in the critical engine disc rupture, turbine burst area occur, seal valves in conjunction with the shuttle valve will automatically isolate the defective side, and oxygen supply will be maintained via the second line. Three quick-donning masks are installed in the cockpit. With oxygen supply at the mask, the crew can choose between 3 different operating modes. Via a switch, they can select the normal mode, which provides an oxygen-air mixture depending on altitude, the 100% mode, which provides 100% oxygen regardless of altitude, and the overpressure mode, which provides 100% oxygen with overpressure to prevent smoke or fumes entering the mask. Smoke goggles are also provided with each oxygen mask. They are supplied with overpressure oxygen from the mask to prevent any smoke from entering. In case of a cabin pressure loss at high altitude or altitude sickness, oxygen is supplied to the flight attendant and each passenger position. Via the solenoid valves, oxygen is routed to the dropout oronasal masks that will drop down automatically at a cabin altitude greater than 13,800 feet. The system can also be operated manually from the cockpit by the use of the separation valve behind the captain's seat, and it can be isolated when not required. Should a leak in the critical engine disc rupture turbine burst area occur, seal valves in conjunction with the shuttle valve will automatically isolate the defective area, and oxygen supply will be maintained to the remaining areas. The dropout units house the passenger oxygen masks and are installed above each passenger and the flight attendant seat. The units will open automatically as soon as oxygen pressure is supplied to them. As soon as the mask is pulled down, the lanyard will disengage the release pin from the manifold, and oxygen will start to flow to the mask. Three first aid oxygen masks are provided, which are normally installed in the forward tapered hat rack. 4 first aid oxygen outlets are installed in the cabin, 3 in the ceiling, and 1 at the flight attendant seat near the entrance door. This allows for supply of first aid oxygen at any position in the cabin. Operation of the passenger system is normally automatic. If the cabin altitude exceeds 13,800 feet, the system will be activated and the oxygen masks will drop out. In case of a failure of the automatic function, or if desired, the pilot can also manually activate the solenoid valves by selecting the switch to manual. If required, the system can be turned off by pushing the PAX supply switch light to off. And in case of an electrical failure, the crew can supply the passengers with oxygen by operating the separation valve. Indication for the oxygen system is provided on the CAS field, the CPCS oxygen system page, and the red warning panel. The oxygen quantity indication on the system page is done in percent, and 100% corresponds to a pressure of 1,850 psi. If the pressure falls below 80%, the oxygen quantity low messages on the CAS field and the CPCS oxygen system page will come on. The oxygen quantity fail message on the CAS field and the system page will illuminate in case of a sensor or wiring failure, and the oxygen lamp on the red warning panel, the crew pressure low, and the passenger pressure low messages will illuminate if the supply pressure to the crew and or passenger system is insufficient. The blue oxygen dropout auto message on the CAS field illuminates below 15,000 feet, when the landing field elevation is selected to above 13,000 feet, or when the cabin altitude is above 9,000 feet. They are reminders to the crew to lock the passenger system. Further flow indicators are installed on each crew and first aid oxygen mask. These indicators are red when no flow is present, and turn green when oxygen flow is present. Protective breathing equipment hoods are installed to provide oxygen supply and protection when moving around the aircraft in case of smoke or fire. The PBE hood is located in a storage box and vacuum sealed. It has a life of 10 years, provided the vacuum seal is not broken. The PBE hood is a self-contained breathing equipment, and it produces oxygen by the use of a container filled with potassium superoxide, or KO2. The exhaled carbon dioxide is also absorbed by the KO2 container, and the PBE hood can supply oxygen for about 15 minutes when activated. Each engine drives a dual-acting, constant-speed feathering and reversible pitch propeller. The pitch ranges from feathered through zero pitch to full reverse. The propeller system is comprised of the following components: the propeller assembly, the propeller control unit, also called PCU, which regulates the oil pressure to the propeller assembly, the propeller high-pressure gear pump, which is mounted on the reduction gearbox accessory drive cover, the propeller overspeed governor, which is mounted on the propeller high-pressure gear pump, the DC electrical-driven auxiliary feathering pump, used for propeller feathering operations, the power lever and condition lever linkage between the PCU and HMU to regulate the propeller blade angle and propeller RPM. The Hartzell 6-blade dual-acting propeller is a constant-speed, hydraulically actuated propeller with feathering and reversing capabilities. The propeller is constructed of a two-piece aluminum hub with composite blades. The composite blade is made up of a titanium blade shank retention section with a blade pitch change knob assembly, into which is molded a low-density foam core that supports built-up layers of composite laminate. A nickel erosion shield is fabricated into the leading edge to protect the blade against impact damage. When looking at a cross-section of the propeller blade, the leading and trailing edges are made of solid composite material. The blade center is made of low-density foam, and the entire blade is covered by laminated layers of composite material. Propeller blade pitch is controlled by the main piston and cylinder combination, mounted on the forward flange of the propeller hub. High-pressure oil is supplied to the propeller via the oil transfer tube. The pitch control rod incorporates a valve that meters the oil to one side of the piston while draining an equal amount of oil from the opposite side. High-pressure oil forced into the cavity between the piston and the hub moves the piston forward from high to low pitch. The high-pressure oil forced into the cavity between the piston and the cylinder moves the piston aft from low to high pitch. The linear motion of the piston is transmitted to each blade assembly through a pitch lock fork and a blade pitch change knob assembly, which will cause rotation of all 6 propeller blades at the same time. In the event of an oil pressure loss, a mechanical pitch lock mechanism has been incorporated into the system to prevent an overspeed condition of the propeller. In the dual-acting control system, the airplane has a shaft-driven, high-pressure pump mounted on the aft side of the engine reduction gearbox. Its function is to increase engine lubrication oil pressure to a level capable of operating the propeller piston, and to supply control oil pressure to the servo cylinder via the overspeed governor and the constant speed unit. The overspeed governor is mounted on the rear of the high-pressure pump. The unit is factory adjusted to provide the correct oil pressure and flow required to operate the propeller control system. The overspeed governor has three functions: monitoring the free turbine RPM, and in the event of propeller overspeed, reducing the oil pressure supplied to the PCU and propeller actuator, which increases blade angle and results in a lower propeller RPM. Allows for ground test of the overspeed governor by use of a speed reset solenoid valve. Protection of the engine against propeller overspeed by an air bleed orifice incorporated into the unit, which bleeds P3 signal pressure from the HMU, and thereby reducing the fuel flow and engine RPM. Whitney Canada PW119B is a turboprop engine with modular design and consisting of the reduction gearbox module and the turbo machine module. The turbo machine is a 3 concentric shaft design, housing a centrifugal high-pressure compressor driven by the single-stage high-pressure turbine, a centrifugal low-pressure compressor driven by the single-stage low-pressure turbine, and a 2-stage power turbine and drive shaft, which is connected to the reduction gearbox input shaft. The combustion system consists of an annular reverse-flow combustion chamber, 14 fuel nozzles, and a dual-ignition exciter system. The reduction gearbox is a twin lay-shaft design containing the first and second stage reduction gears and the offset propeller shaft. The reduction gearbox used for reduction of the engine power turbine speed consists of the following housings: reduction gearbox front housing, reduction gearbox rear housing with accessory drive cover, and input drive housing. The reduction gearbox front housing holds the front roller bearings of the 2 second stage gear shafts and the front roller and thrust bearings of the propeller shaft. The reduction gearbox rear housing holds the rear roller bearings of the 2 second stage gear shafts and the rear bearing of the propeller shaft, as well as the front roller bearings of the 2 first stage helical gears, the front bearing of the input shaft, and the front bearings of the accessory drive shafts. Torque tube mounting pads are located at the 5 and 7 o'clock positions of the rear housing, and the side mount mounting pads are located at the 3 and 9 o'clock positions. The reduction gearbox input housing holds the rear roller bearings for the 2 first stage helical gears and the rear bearing of the input shaft. The accessory drive cover houses the rear bearings of the accessory drive shafts and also provides mounting pads for the AC generator and the PCU hydraulic pump. The turbo machinery consists of 4 sections contained in 6 casings. The air inlet section consists of the front inlet case, which is bolted to the reduction gearbox, and the rear inlet case, which is bolted to the diffuser case. The front and rear inlet cases are bolted together at the 2 flanges. At the top of the front inlet case is a torque sensor mounting pad. The ECU and torque signal conditioner unit are mounted on the left side of the case. The ignition exciter boxes and the fuel flow transmitter are mounted on the right side of the front inlet case. At the rear inlet case, the fuel pump and HMU are mounted on the front side of the accessory drive gearbox. The starter generator is mounted right next to the fuel pump and HMU. The reduction gearbox oil filter housing is mounted on the lower side of the rear inlet case, next to the oil pump pack, which houses the oil pressure and scavenge pumps. On the left side of the rear inlet case, the oil-to-fuel heater is mounted above the main oil filter housing. The integral oil tank is housed in the lower side of the rear inlet case and is equipped with an oil level indicator and an oil filler neck for oil tank refilling. The compressor section comprises the low-pressure centrifugal impeller, which is mounted into the low-pressure diffuser case, and a high-pressure centrifugal impeller, which is mounted into the intercompressor case. The low and high-pressure compressors are interconnected by externally mounted diffuser pipes, which guide the air from the low-pressure compressor outlet to the high-pressure compressor inlet. The accessory drive of the rear inlet case is driven via an angle drive by the high-pressure impeller. A bevel gear mounted on the front end of the high-pressure impeller drives the rear inlet case accessory drive gearbox, the starter generator, and fuel pump via an angle drive gearbox. The oil system is a wet sump type system with the following main components: an integral oil tank within the rear inlet case, an oil filler neck with cap for refilling the oil system, an oil level indicator to visually check the oil level within the tank, an oil low pressure switch for cockpit warning, and an oil pressure transmitter for cockpit oil pressure indication. The pressure regulating valve assembly regulates the engine oil pressure within the engine lubrication system. A filter and filter bypass housing assembly filters the pressurized oil, or bypasses the oil in case of a filter blockage. An impending bypass switch will detect an impending filter blockage. A check valve is mounted on the filter housing to prevent oil flow to the bearings number 3, 4, 5, 6, and number 7 below 25% NH. The check valve also provides a location for an oil temperature sensor, which is used for oil temperature indication. The pressure oil pump, which is part of the oil pump pack, sucks the oil from the oil tank via a magnetic chip detector, which detects metal particles in the oil, through the high-pressure relief valve, which prevents a pressure surge during cold weather starts, to the airframe oil cooler. By a flexible oil line, the oil flows from the high-pressure relief valve to the airframe oil cooler, where the oil is cooled to normal operating temperatures. The cooled oil leaves the oil cooler by a flexible oil line to the oil inlet of the oil filter housing. Oil from the oil filter housing is guided into the oil-to-fuel heater to heat the fuel and eliminate possible ice crystals. From the oil-to-fuel heater, the oil flows through an external oil tube to the reduction gearbox. From the external oil tube, the oil enters the reduction gearbox and is internally distributed from the reduction gearbox integral oil tank to the PCU pump, which increases the engine oil pressure for propeller pitch controlling, the propeller overspeed governor, which protects the propeller against overspeed, the auxiliary feathering pump, which is used to feather the propeller, and to the reduction gearbox internal gears and bearings. The reduction gearbox is scavenged by an oil pump mounted in the oil pump pack and draws the oil from the bottom of the reduction gearbox, passing a magnetic chip detector, which detects metal particles in the scavenged oil. The oil then flows through a line which is looped upward to prevent oil from the reduction gearbox from flooding the oil tank when the engine is not running into an oilway in the front inlet case to provide anti-icing of the intake. Leaving the front inlet case will flow through an external oil line into the reduction gearbox scavenge pump, which is part of the oil pump pack. The oil then flows into the reduction filter housing, where the oil is filtered and returned to the oil tank. The filter housing is equipped with an impending bypass switch to warn of impending filter bypass. The turbo machinery scavenge oil system consists of only one mechanical scavenge pump, which is part of the pump pack. The engine oil system is vented by a centrifugal breather, which is mounted inside the rear inlet case. The breather separates the air from the oil and vents the air by an external line into the exhaust. By turning the starter generator, the pressure oil pump will be driven via spur gears and sucks oil from the oil tank passing a chip detector. A pressure relief valve returns oil to the tank to prevent a pressure surge during cold starting. The airframe oil cooler bypasses the oil until above normal operating temperatures are achieved. Oil from the oil pump flows through a 10-micron high-pressure oil filter. In case of a filter blockage, the oil will be bypassed through the filter bypass valve, and at the same time, the impending bypass switch will be closed. From the oil filter, the oil flows in two directions, to the oil-to-fuel heater and reduction gearbox, and to the check valve housing. Before the oil enters the check valve, a part of the oil is guided to the number 1 and number 2 bearing cavity, the accessory gearbox, and the angle drive gearbox for lubrication of the gears and bearing. During engine starting and shutdown, the valve stops oil from going to the number 3, 4, 5, 6, and number 7 bearings, ensuring that sufficient pressurized air is available at the bearing labyrinth seals. The check valve opens when the oil pressure overcomes the check valve spring pressure. This spring pressure corresponds with approximately 25% NH. The lubrication oil then flows to the number 3 and number 4 bearings, the number 5 bearing, and the number 6 and number 7 bearings. In the check valve housing, a temperature sensor is mounted for oil temperature indication. Oil pressure is measured by the oil pressure transmitter, mounted between the oil pressure line of the number 6 and number 7 bearings, and the air pressure of the number 3 and number 4 bearing cavity. For this reason, the oil indicator shows oil pressure in PSI differential. The low oil pressure switch is located in the same loop as the oil pressure transmitter, and gives a warning in case of low oil pressure. Pressure oil which is sent to the main bearings will be scavenged back to the oil tank as follows. Oil from the number 1 and number 2 bearings is scavenged by gravity and falls back into the oil tank. Oil drainage from the number 3, number 4, and number 5 bearings is assisted by air leakage from the bearing labyrinth seals and is blown back into the oil tank, a drainage method called blowdown. The oil from the number 6 and number 7 bearings is scavenged back into the oil tank by a scavenge pump, which is part of the oil pump pack. The oil tank and the number 1 and number 2 bearing cavities are vented internally. The number 6 and number 7 bearing cavities are vented externally into the accessory gearbox. A centrifugal oil separator, which is installed in the accessory gearbox, removes oil before vented air is discharged into the atmosphere. Oil flows along a tubing connection from the oil-to-fuel heater into the reduction gearbox integral oil tank. This tank is pressurized and always full of oil, even when the engine is not running. Oil from this tank flows by internal passages to the electrical feathering pump, and when the pump is activated, oil pressure will be delivered to the propeller control unit. The PCU pump, which is driven by the reduction gearbox, also sucks oil from the integral oil tank and boosts the oil pressure, sending this to the PCU and actuator for normal propeller pitch change operations. Oil from this tank is also distributed for lubrication of the reduction gearbox gears and bearings. The overspeed governor sends a signal pressure to the PCU, and in case of a propeller overspeed, the propeller system pressure oil will be bled into the scavenge system. The reduction gearbox bearings and gears, PCU and propeller actuator drain oil into a cavity at the lower side of the reduction gearbox housing. The reduction gearbox scavenge pump sucks the oil from the cavity through a chip detector, which detects metal particles in the oil. From the scavenge pump, the oil flows through the reduction gearbox scavenge filter into the oil tank. In case of a filter blockage, the scavenge oil will be bypassed through the filter bypass valve and will be returned to the oil tank unfiltered. At the same time, the impending bypass switch will be closed. The pressure-regulating valve consists of a piston and spring in a ported sleeve. It maintains a constant oil pressure above the air pressure in the number 3 and number 4 bearing cavity, and oil pressure from the number 1 and number 2 bearing cavity. If oil output pressure taken from the number 1 or number 2 bearing cavity overcomes the air pressure plus spring pressure, the valve opens a port, and oil from the main pressure line is bled back to the oil pump inlet, and reduces the oil pressure in the pressure system. The engine fuel system performs in the following way. Fuel from the aircraft fuel tank enters the engine at the oil-to-fuel heater, where the fuel is filtered and heated to eliminate ice crystals in the fuel. From the fuel heater, the fuel passes the fuel low-pressure switch, which gives a cockpit warning in case of low fuel pressure, and a temperature sensor, which indicates the fuel temperature in the cockpit gauge. The fuel then enters the fuel pump, where the fuel pressure will be increased and filtered before the fuel flows internally to the HMU. The HMU will meter the fuel for the correct engine requirements, and will also bypass high-pressure fuel for the motive flow system. Metered fuel from the HMU passes via the fuel flow transmitter, which indicates the fuel consumption in the cockpit, to the fuel flow divider, which is mounted on the fuel inlet manifold. The flow divider separates the fuel into a primary and secondary flow to the 14 fuel nozzle adapters, which are installed in the gas generator case. During engine operation, fuel is pumped from the aircraft fuel tank to the engine fuel inlet by either or both the electrical fuel booster pump and the ejector pumps. Fuel is introduced into the engine fuel system at the fuel heater, where the fuel flows through the low-pressure fuel filter. In case of a filter blockage, the fuel will be bypassed through the filter bypass valve, and at the same time the impending bypass switch will be closed, and a caution message in the cockpit will illuminate. The fuel then flows through the heat exchanger, where the fuel is heated by engine oil to eliminate possible ice crystals. The fuel heater regulates the oil flow through the heat exchanger to preheat the fuel to the normal operating temperature. The heater housing consists of two circuits, a lubrication oil circuit and a fuel circuit. A thermal sensor in the fuel flow circuit detects the fuel temperature and opens or closes the oil bypass when the fuel temperature changes. Oil from the main oil filter flows into the heat exchanger via the bypass valve back into the lubrication system. At fuel temperatures below 10 degrees Celsius, the bypass valve is fully open, and max oil flow will be obtained through the heat exchanger. At fuel temperatures above 10 degrees Celsius, the bypass is closed, and oil flow through the heat exchanger is reduced. At fuel temperatures above 32 degrees Celsius, the bypass valve is fully closed, and oil flow through the heat exchanger is bypassed. Fuel from the oil-to-fuel heater flows via an external transfer tube to the fuel pump, through a self-relieving strainer, into the positive displacement pump. This pump sucks the fuel from the aircraft fuel tank during engine startup and is driven by the starter generator. High-pressure fuel from the pump then flows through the high-pressure fuel filter to the HMU. In case of a filter blockage, the fuel will then be bypassed through the filter bypass valve, and at the same time the impending bypass switch will be closed and a warning will be sent to the cockpit. High-pressure fuel from the fuel pump flows internally to the HMU, where the fuel will be separated into 3 flows. One flow is directed via the motive flow valve to the tank ejector pumps to assist the engine-driven fuel pump. Motive flow is also sent to the drain tank ejector pump for scavenging the drain tank to the inlet of the fuel pump. The second flow is sent back to the motive flow pump, which increases the fuel flow to the positive displacement pump. The third flow is metered by the HMU to the correct fuel flow for engine operation. Metered fuel from the HMU passes the fuel flow transmitter, which measures the amount of fuel flowing through the metered flow circuit, to the flow divider, which is mounted on the fuel nozzle inlet adapter. The flow divider separates the fuel flow between the primary and the secondary fuel nozzles, and also dumps the fuel from the fuel nozzles at engine shutdown. The engine indicating system consists of sensors and probes to control and monitor the engine during operation. The propeller speed sensor mounted in the reduction gearbox senses the propeller speed via an idle gear whose speed is relative to the propeller speed, and sends this signal via the EEC to the cockpit indicator. The torque sensor mounted into the front inlet case senses the amount of torque on the torque shaft, and sends this signal to the TSCU and the cockpit torque indicator. The torque shaft assembly mounted between the P2 shaft and the input shaft of the reduction gearbox consists of a torque shaft and a reference shaft. The 2 shafts each carry a toothed wheel and are both secured at the rear end only. For each tooth passing near the magnetic pulse pickup torque sensor, a sine wave is generated. This signal is sent to the TSCU. Twisting of the torque shaft relative to the reference shaft is proportional to torque transmitted. The indicated torque is thus proportional to the ratio of the torque shaft and the reference shaft. The high-pressure compressor speed sensor mounted on the rear inlet case senses the speed of the starter drive shaft, which is relative to the HP compressor speed. This signal is sent via the EEC to the HP compressor speed indicator. The low-pressure compressor magnetic speed sensor is mounted into the intercompressor case and senses the LP compressor speed at the lock nut of the number 3 bearing. This lock nut has teeth at the outside diameter and passes the NL sensor. The signal, which is generated by the passing teeth, will be sent to the cockpit NL indicator. For measuring ITT, thermocouples are mounted in the turbine support case and measure the temperature of the hot gases between the LP and power turbine, called Station 6. The thermocouple probe consists of an alumel and a chromel part, which are connected together at the probe tip. When alumel and chromel are heated, an electrical current is generated. To measure a more accurate temperature inside the engine, for measuring ITT, thermocouples are mounted in the turbine support case and measure the temperature of the hot gases between the LP and power turbine, called Station 6. The thermocouple probe consists of an alumel and a chromel part, which are connected together at the probe tip. When alumel and chromel are heated, an electrical current is generated. To measure a more accurate temperature inside the engine, 9 thermocouples are installed and connected in parallel by a bus bar. The average and more accurate temperature is sent to the cockpit ITT indicator. The electronic components of the fuel control system are comprised of the Torque Signal Conditioner Unit, also named TSCU, and the Engine Electronic Control, also named EEC. These two units, in conjunction with various sensors and the HMU, provide a limited authority automatic control over the engine. During normal operation, the TSCU transmits signals to the EEC of its own engine and to the TSCU of the twin engine. If the auto feather system is selected and armed, and an engine should fail, its TSCU will initiate its engine's auto feather system and signal the EEC and TSCU of the twin engine. In this event, the EEC of the twin engine increases power to compensate for the failed engine. The twin engine TSCU disables its auto feather system to ensure both engines are not feathered at the same time. The EEC monitors the engine operating condition through various inputs from both airframe and engine as follows. These inputs comprise power command from the power mode selector, power lever angle from the HMU potentiometer, torque from the TSCU, and ambient pressure PO and total inlet pressure P1.8 from the transducers contained in the EEC. The EEC also receives HP rotor speed, propeller speed, and total inlet temperature T1.8 from engine-mounted sensors. These inputs are processed by the circuits in the EEC and compared with reference data stored in the unit's memory. From these, commands are generated and transmitted to the torque motor in the HMU to adjust the fuel flow and the torque bug on the torque indicator. The torque needle is then matched to the bug by adjusting the power lever. The EEC also contains a built-in capability, which in event of an internal fault will change the system to manual control and energize a warning light. In addition, the system will revert to manual when the NH overspeed circuit operates or the EEC is switched off. The ignition system provides a quick light-up capability over a wide temperature range. It requires a nominal 28-volt DC to operate, but can function on 16 to 30 volts. The system comprises 2 ignition exciters, 2 individual high-tension cables, and 2 spark igniters located at the 5 and 7 o'clock positions on the gas generator case. The auto-ignition procedure during flight is achieved automatically when the auto-feather system commands the propeller into feather. As a precondition, the landing gear must be retracted. In addition, none of the buttons for engine fire can be pushed, and the condition lever must be in the position minimum RPM. If the engine speed now decreases lower than 60% NH, the ignition exciters are energized, and the spark igniters will ignite the air and fuel mixture. At the same time, the start annunciator in the switch light will illuminate. This procedure is ended as soon as the engine speed increases to more than 60% NH. Engine starting is done with an electrical 28-volt DC starter generator mounted on the right side of the accessory gearbox. Via drive shafts and bevel gears, the starter generator drives the high-pressure compressor, which then will compress the incoming air. When a certain high-pressure compressor speed is reached, fuel will be sprayed into the combustion chamber, where it is mixed with the incoming air. This mixture will then be ignited by the igniter plugs, and the expanding gases will start to drive the turbines. The high-pressure and low-pressure turbines are directly connected to the high-pressure and low-pressure compressor, which now will start to draw in more air for combustion. This will cause the speed of the turbines to increase, and when the speed required for self-sustained operation has been reached, the ignition will be switched off, and the starter will be used as a generator. Engine starting is performed by first setting the vent off start selector to start, which will supply electrical power to the start button. When the start button is then pushed, the start annunciator will illuminate. The starter generator will start to operate, and the ignition is turned on. When the minimum NH required for starting is reached, fuel flow can be opened. The engine will start to accelerate, and all parameters will increase. As soon as the engine NH reaches 45%, the starter function and ignition will be turned off. The engine will then accelerate and stabilize at idle power without starter assistance. For ventilation of the engine after a hot start or a hung start, the vent off start selector can be selected to vent. Pushing and holding the start button will cause the starter to operate. Note that the button should not be pushed for more than 15 seconds.